Hello everyone and welcome to our workshop on map-based localization for autonomous driving. This workshop is being held in conjunction with ECCV 2020 and this is the afternoon session. It's my great pleasure to introduce and welcome everyone on behalf of all our organizers. Our organizers include Daniel Kremers, who is heading the Computer Vision and Artificial Intelligence Lab at Technical University of Munich, and he is also a co-founder and chief scientific officer of Urtasun Corporation. Urtasun is commercializing visual odometry and SLAM solutions for the industry. Ray Wang and Nan Yang are also PhD students at the same lab and also researchers at Urtasun. Niklas Zeller is research lead at Urtasun, and my name is Patrick Wenzel. I am also a PhD student at TUM as well as a researcher at Urtasun. A short information about this schedule for today. So we will have this live stream on Zoom, and we also do encourage to ask questions on Zoom during the talks of the pre-recorded invited speakers. We would have Q&A sessions followed after the talks. We also do plan to stream this event to YouTube after ECCV. If you want to have a look for a detailed schedule, please look at our webpage. For a short overview on our workshop, so this is the first edition of the workshop which is being held at ECCV 2020. And the focus of this workshop is on map-based localization for autonomous driving. We wanted to introduce this new workshop in order to focus on topics mainly centered about visual, indirect, and direct SLAM approaches, robust visual localization algorithms for changing conditions, in particular weather, day and night changes. Also, we wanted to have a look at self-supervised and semi-supervised learning approaches, domain adaptation, and of course, mapping and localization. This workshop features 5 invited keynote talks. We have 2 talks by the challenge winner and runner-up of our visual relocalization challenge. We had 1 tech talk already in the morning session and 1 peer-reviewed workshop paper also in the morning. So in the morning, we had Dengqing Dai from ETH Zurich, as well as Andreas Geiger from the University of Tübingen and MPI for Intelligent System. In the afternoon session, we will start with a talk from Stefan Leutenegger from Imperial College London, followed by a talk from Raquel Urtasun from Uber ATG and University of Toronto. And we will conclude this workshop by a talk from Cyrill Stachniss, who is affiliated with the University of Bonn. As I mentioned, we had this workshop already in the morning. Feel free to have a look at the ECCV online platform to have a look at the contributed paper talks and also the invited talks from the speakers. So how is the afternoon being structured? So right now we are starting with a short introduction, followed by an invited talk from Stefan Leutenegger, which is followed from at 4:50 approximately from an invited talk for Raquel Urtasun. And then at 5:30, we would have our relocalization challenge winner talks, where the first place is at 5:30, Paul Eduard Salin and others, with the title Hierarchical Localization with HLOC and Superglue, and the second place talk from Yaroslav Melekov, Image Stylization for Robust Features. We will conclude this workshop today by an invited talk from Cyrill Stachniss. A short introduction about our visual relocalization challenge. So we have built a reference map by visual inertial odometry fused with RTK GNSS to obtain precise reference poses. We do provide reference and target pairs for relocalization, and we capture our images with the stereo camera system. Particular for this challenge, we provided 5 different traversals of the same scenario, and the data we used for this challenge is a part of a later dataset which will be published later this year at GCPR 2020. So in this slide, you can see a glance of our part of the data. On the top of the slide, you see the 3D reconstructed map, and on the bottom, you can see 3 images captured from our moving vehicle on different day and different times. So you can also see structural changes. For example, on the left image, you can see also like a small construction zone, you have to deal with these kind of changes and auto lighting changes. So for the submission, we provided 2 test sequences from different conditions where we provide easy, moderate, and hard samples. And we also did already provide a reference and query frames. And the task was to estimate the relative 6-degree of freedom pros between reference and query frames. For the challenge, we withheld the ground truth, and the evaluation was done by submitting text files to the organizers. And we had one requirement that we need a paper including archive available by the submission deadline. I would also like to thank our workshop sponsors for providing prize money for the winner, which is $1,000 and for the second one, which is $500. So thanks a lot to our workshop sponsors, Artisans and Kudan. So with these words, I would like to conclude the introduction, and I hope you will enjoy our afternoon session. Thanks a lot. It is my pleasure to introduce Stefan Leutenegger, who is a senior lecturer in robotics at Imperial College London. And besides leading the Smart Robotics Lab, he is also co-leading research projects at the Dyson Robotics Lab together with Professor Andrew Davison. Stefan received a Bachelor of Science and a Master of Science in Mechanical Engineering from ETH Zurich in 2006 and 2008, and also a PhD in 2014 working at the Autonomous Systems Lab of ETH Zurich. His research is centered around autonomous robot navigation. This includes localization and mapping with a suite of sensors, most importantly cameras, to be processed efficiently to yield accurate results at real time. I'm very much looking forward to his talk.
Hi everyone, my name is Stefan Leutenegger and I'm a senior lecturer at Imperial College London. Thank you very much to the organizers of this workshop on map-based localization for autonomous driving to have me here and give a talk. I have to warn you though that I'm not actually doing research on autonomous driving, however on mobile robotics, and so I'm going to talk a little bit more generally about map-centric and robust mobile robotics, and then hope that some of the things that I say are transferable to autonomous driving as well. So just to start with a little example that we put together a couple of years ago now with my lab. Here's a drone that is flying fully autonomously. This was actually for a challenge, for a robotics challenge, where it had to really be power on and go, one button press, the drone takes off autonomously. It can use only its onboard processing here. So we have a kind of Intel NUC up there. Then there is an RGBD and inertial camera mounted to it as well. That would then actually do visual inertial slam, sparse visual inertial slam on board. And then there's also a downward looking camera here. And the task of that one was to spot a moving vehicle. So find a moving vehicle, then track it, approach it, and actually land on it. And so here's how it works. Drone takes off autonomously, goes around and tries to find that moving vehicle. We're simulating here. And so the downward looking camera spots it, gets the drone to approach and land, and that works. So the difficult bit is though to not just make it work once, but in all kinds of circumstances, in all kinds of visual circumstances, as well as here from different kind of wind conditions and so on. So that's a tricky bit really, to make it work in a robust way. So while this is an application of robotics that works to some degree, I think it's good to take a step back and look a little bit at all the applications that there are and how well they work. So I put some of the interesting ones, let's say, into this plot. Obviously not everything is here, but as you can see, I put the Ambizirk drone that I've just shown here on the left. And this is a plot that comprises 2 important axes, I think. It comprises how narrowly the task is defined versus very open-ended and complex on the one axis, and then about the environment on the other axis. How open-ended is the environment, or how controlled and very specific is it? And I think it's quite clear to see here. So what's green is stuff that's currently kind of working, right? The things that are kind of working are on the sort of bottom left side. Whereas as soon as you go towards very much open-ended like environments and open-ended complex tasks, things become difficult and are not yet feasible. And I would argue that some of them are quite a long way away actually. And so this is where I briefly talk about autonomous driving as well. As you can see, there are actually 2 data points of autonomous driving in here. One is autonomous driving in a very specific modified infrastructure where you have full control. Maybe you don't allow pedestrians on there, you geofence it, you put up sensors and beacons and so on, and that's absolutely feasible right now. Whereas the kind of autonomous driving anywhere in the world on the current infrastructure, I would say, is still very far away. But there's true experts here in the speaker, so feel free to disagree with me on that one. There's also things like a general household robot up there on the top right. I think that's quite far away, or a delivery drone that we haven't quite seen yet, which would have to operate in a quite open-ended environment in our everyday environment. Okay, so let's have a bit of a more technical look at how robotics is being done. And I appreciate that I'm probably preaching to the choir with this slide, but this is very much the kind of traditional robotics, mobile robotics approach that I have here on the left, the classic kind of modular approach where you take some sensor inputs, you process them in some way, you do some form of state estimation mapping, you feed them to some kind of higher level planning and ultimately motion control, and the whole thing repeats. And then you may have some knowledge on board that robot, you build up a map, or you have a previous map and objects and so on. And that allows you as a user, as a roboticist as well, to quite intuitively interact with this thing, because it uses the concepts that you will have engineered, and so you can introspect it also while it's operating. At the same time, though, I think the main problems why some of these applications that I've shown before on the slide before aren't quite working is actually that there are still some significant gaps, and they're typically about processing sensory information into some form of representation that's just not quite good enough and not quite sufficient, and then the whole cycle here, the whole control cycle, can break down. And of course, the appealing thing of using a very much in fashion kind of more black box-ish end-to-end approach that directly maps sensing to actions has the advantage that there isn't such a gap. So it seems appealing to do such a thing. You can get some self-emergent, not handcrafted type of behavior out of this. But of course, at the same time, it's quite obvious that you lose the kind of introspection. You end up with a much more black box kind of approach here. And I think, though, the more critical point about this is perhaps why it's not suitable for the tasks on the sort of upper right corner in my graph before, where you are dealing with very general stuff, very general tasks, very general environments, is that to do this kind of general, to train these kind of very general tasks, we're probably not quite data efficient enough with such a purely end-to-end learning-based approach. So that's why for the rest of the slides, I'll be arguing for a sort of in-between kind of approach where we are borrowing the very strong concepts, of course, that you get in learning, and we're trying to fill the gaps in here in our more traditional kind of cycle. So clearly then, spatial AI or some form of map representation will be at the center of these types of robots that are going around in our environments. And I like to think of them as different levels of capabilities that we need to give our robots. So a very basic one is perhaps just focused on motion tracking, about tracking position and orientation, perhaps some other states. Is not so much about the map. You might be building up a sort of sparse map to do then sparse visual inertial localization in there, but it's a side product. It's not really the goal of what you're doing here. It just enables you to do accurate tracking in 6D. And you can already do quite a lot of things. For instance, the drone that I've shown before, as long as you know that the world is flat, you can use this approach, and you don't really need more of a map to achieve that. However, of course, for much more interesting applications, you will want some form of a much more expressive representation of the environment. And so dense mapping has come along in my research with my group, also in collaboration with Andy Davison from the Dyson Robotics Lab. We have been intensively looking at that, dense mapping, and then also how it can actually benefit the robot, how it can be used for motion planning, collision avoidance, or some simple form of physical interaction. Clearly, you will want to do more, and this is where learning can come in. You can now start to understand really the 3D scene at the level of semantic labels. Semantics labels that allow you to do more advanced task planning for a robot, and also a much more interesting human-robot interaction, where, for instance, you could tell a vacuum cleaner robot here to go clean the bed or clean the floor underneath the bed, which clearly with a purely geometric one you could absolutely not do. But it's also still not enough for more advanced stuff, and certainly autonomous driving belongs into that category. You need a sort of object level awareness. You need also an awareness about dynamics, about motion, and you will want to have this concept of individual objects that you are detecting and tracking over time, and that allows you more advanced physical interaction between the robot and an environment. For instance, also allows you to do manipulation or much more advanced, much more interesting human-robot interaction. So I'll be just briefly talking about two of these examples here. And then we'll be talking about how these concepts can be used to actually control a drone in a little bit more detail again. So here's an example about how to do dense mapping that actually scales. So it comes really down to what is the right representation to do that. How do we want to encode space? And so recently we have been doing a lot of work in volumetric approaches where to make it scale, we adopted this concept of octree-based mapping. That's of course not a new concept per se, but it turns out it's really useful also in the context of mobile robotics, where you want to do free space queries and to do motion planning and collision avoidance. So the concept also very much leans itself to this idea of hierarchical representations, of adaptive resolution mapping, which is really an advantage of using something like an octree as opposed to some more flat hashing strategy or so, because very naturally already in the data structure here, since it is hierarchical, you can actually represent say a TSDF field or an occupancy, Logot's occupancy field. You can directly encode it at different levels of resolution, where basically the coarse resolution is then just consistently going to be maintained as the mean of the children, ultimately in the octree of the 8 children, one level finer. And this allows you to do mapping in a way that avoids aliasing. So you can integrate information along array at different distances using the correct scale, using the scale that is corresponding to the kind of mini frustum of 1 pixel. And at the same time, also at the tracking level, you can do the same. You can adopt the same scheme of representing the world at the right kind of coarseness that you need. So this has several advantages in terms of accuracy and speed that I will go in a bit more detail in a bit. But first, just a couple of examples of how this works in practice. So here you can see on the left the kind of color encoding of the current scale that is being selected as a function of the distance to the camera. So red would be sort of a coarser level, green is the finest level, and then blue is yet one level coarser. And on the right side, you can see that we can also integrate colors. We can do color fusion that in fact also adopts this hierarchical kind of scheme. So this is doing dense ICP-based tracking. So here we're using a depth camera. and then of course the color camera for color fusion on the right. So here's just an illustration of the kind of accuracy gains that you get. Just if you compare to using a straightforward implementation of effectively Kinect fusion, you can really start to see the benefits in terms of the details that are being preserved in this case, as opposed to the straightforward single resolution approach. And that will actually happen when you're moving the camera sort of in and out of the scene. That's really when you can start to see these kind of benefits from the approach. Also a bit more quantitatively, in terms of tracking, you get more accurate results. You get definitely also very competitive results in comparison to state-of-the-art methods like Infinitam that we compared here. And on the right-hand side, you can see the gains in terms of computational power. And I think that's part of why this is really interesting to use these hierarchical schemes. That in comparison again to a single resolution baseline approach, still as an octree based approach, straightforward implementation, but without the adaptive resolution scheme, we get significant speed ups in the order of a factor of 2, 3, 4. Okay. Now we can also use, of course, these things to go up the levels that I initially mentioned. So we have adopted this scheme of octree-based volumetric mapping to decode, to represent the scene as individual objects that can move with respect to a static environment. So in this system that is called mid-fusion, you can see now how individual objects are being moved around. The camera is also being moved around. So you have to actually do SLAM for the camera with respect to the static environment, and at the same time then detect and map individual objects. So this is the kind of most difficult of cases here that we're tackling, where we actually don't make any assumptions about either camera motion or the static world or the individual objects. So there are no previous kind of CAD models available or so. And of course, there may be many cases in reality where you would have such models available, but we wanted to see how far you can go by actually not knowing anything in terms of geometry about the objects. Now, of course, to detect the object and kind of bootstrap the whole process of mapping, we very much now rely on deep learning. So using mask RCNN here to do this process of detecting individual objects and having mask proposals. But then we combine that at the level of tracking the individual objects and also versus static background by analyzing RGB and ICP residuals to decide whether or not an object is static. And then if it is not, to actually find the relative motion between camera and that object. So here's just a couple more examples of how this works in practice. So you can see how now we can simultaneously move quite a lot of these, and you can see how probably this could be quite interesting now to start thinking about doing manipulation of previously unknown objects with a robot. Now, of course, it still doesn't quite reach the kind of accuracy and robustness that we might want. So addressing this kind of issue raised initially about the gaps. So I think there's still a lot of room to be done, of research to be done here to improve that. But now I promised I was going to talk about how these maps can really be used by a robot. And here's a first example. So it's all about doing exploration of an industrial site, for instance, with a drone, where you don't have an initial map perhaps, or not a good enough map. So you want to get a map, you don't want to collide with the environment, and you want the map to be complete, and you of course don't want the drone to crash into anything here. So this is the output of our algorithm, and the way it works is it's using now exactly the kind of octree-based maps I was talking about before in a kind of fully volumetric and 3D occupancy adaptation, where we can maintain full information about what is free space and what is unknown space. And we can also maintain these frontiers now quite efficiently inside this map representation, the frontiers between what is known to be free space and what is unknown space. And we can start to make now plans within the known free space towards the frontier, and select the kind of paths that have the highest potential of exploring as much as possible, as quickly as possible of that map. So we're actually using, again, the same raycasting concept that we already used for tracking and mapping before, to make these kind of decisions, and then kind of iterate these planning iterations. So it's just a good example, I think, of how important it is to have the right map representation to solve a certain task. So it's all about the task, the robotic task here that should guide your choices. And the tight interaction between the map representation and the planner and controller is quite important, as what's making it efficient. So here's a full example of, slightly sped up later on, of how this works to explore a kind of maze. So the drone goes around. This is simulation only now. Goes around and makes these choices about where to go, and at all times has to also avoid collision. Importantly, has to avoid actually flying into unknown space. So we have to be very conservative here. Unknown space has to be treated the same as occupied space. Okay, but of course we wanted to see how this works in the real world. So here's also an example of our drone lab, where we can see drone just been taken off, done an initial observation, initial depth map, and from now on you start planning its behavior, and the behavior kind of really self-emerges from there to complete this whole map. Okay, until it is done at some point. Okay, so now I'm just going to talk a little bit more about drones, and actually also a little bit about control, just to give a bit more details about how we are actually operating the full system, knowing that this is a computer vision conference and perhaps control is slightly out of scope. But I still think it's important and interesting, especially when comparing them, these approaches to kind of the more end-to-end visual input to direct control output type of systems. So here is a bit of details about how the system was working, that was landing on that moving target on top here, where basically we are using a model predictive controller that is modeling the closed loop attitude dynamics of the drone as a sort of gray box linear system, and then we can close the loop using something like visual inertial SLAM, or using OCVIS here to do the visual part. Now, more recently, we have been much more moving towards nonlinear model predictive control, where actually we're really trying to understand the full nonlinear rigid body dynamics of a drone. So there's no need of this kind of cascaded approach and identifying a gray box linear model. We really use the true, well, what we think is the true nonlinear model, and can directly set the rotor commands to get the drone to do what we want it to do. So this approach still involves, if you will, some form of learning, where in fact we have to identify some of the unknown parameters of the model, things like thrust and moment coefficients, inertia matrix, mass, of course, and so on and so forth. But it's a relatively low parametric model, and importantly, it is a model that is generally valid. That is valid for all kinds of states, and not a subset of those that have been previously observed in a kind of training phase. So you can then now take that model, and we formulate this optimization problem as a finite horizon minimization of this kind of cost function, this cost integral, where we penalize position, yaw, velocity, and control inputs. And then, of course, the whole thing is subject to constraints, the constraints being the nonlinear model, as well as our output constraints, ultimately the rotor speeds that are limited. So here's how this now works in action to really get the drone to do quite aggressive stuff. So here's just it's really just this position command. What the drone does then is a sort of entirely self-emergent behavior that is never seen or done before, that just turns out to be in these kind of online optimization steps that are physics aware. The drone is very much self-aware, that turn out to be the best thing to do in order to achieve that task. And just to outline a bit the generality of this kind of model, we can also get the drone to fly upside down, even if it hasn't done that before. Or we can do other interesting things like disabling a motor, and as long as it's aware that the motor is disabled, the model just works just the same way, and we can use the exact same controller, just with different constraints. We can also do things like actually disabling a motor, a rotor, without the drone knowing about it, and having then a model-based estimator that identifies that the motor has actually failed. And again, then it can adapt the controller in this very straightforward way and can keep going. This is sometimes tricky, of course, to save itself before it actually hits the ground, but it works in these kind of constraints. Okay. And that also doesn't work just in hover, it also works when you're actually flying set point commands. It saves itself, and you can still quite safely bring the drone back to landing spot. So I think this is, another component of an overall robustness that we need to achieve if we want these things to be deployed in the real world. Okay, and again, just to outline a little bit that it's not supposed to just work once. It's very important that it works always, and also that you don't get any false detections. So in 16 successive experiments here that we did, we had actually 100% detection recall, 100% precision, and as you can see, we also managed to save the drone. Well, the drone managed to save itself in all of these cases. Okay, so that's just briefly about drone control. Now, maybe a bit more interestingly, how can we also get the drone to interact with the environment? An environment as it may be modeled, for instance, with the kind of spatial AI techniques that I was outlining before. So we put an arm on the same drone here, and we just slightly adapted the control framework to also include end effector, lateral position, and contact normal force. So we wanted to get this drone to write something on a whiteboard. And here you can see how this works. So similar controller, but now augmented with a 2D lateral position to draw the kind of stuff we wanted to draw, and a 1D force controller to maintain the correct pressure to be able to successfully draw something on here. Okay, so this was actually before social distancing and remote teaching and so on. We didn't quite know that this may be a quite timely thing to do actually at this point. Okay. So here it goes, finishing the task. Okay, not perfect, but it's done the job, it's readable. And just to show a little bit, again, the robustness aspect, you really want to be able to do these kind of experiments with some kind of different conditions and successfully in a succession. So this is just, again, to outline a little bit the kind of robustness that we get, even when flying the drone at different velocities. Now here we actually had no visual feedback, and we kind of hard-coded the 3D world, so it wasn't doing any online mapping or so. That's clearly the next step. That's where we want to go. Clearly the drone should be looking at the kind of things it's actually drawing. So the next steps in this kind of work, I think, are quite clear, and they will really link together the kind of spatial AI and control very much. So at this point, I want to conclude just briefly. What I've shown is some approaches to do map-centric mobile robotics, outlining a bit dense and semantic mapping, and then applications to autonomous drones. And I hope I convinced you that really robustness and sufficient accuracy is key to success. And clearly there's also still a lot of room to improve these things. Open challenges clearly all around what really are those right representations, especially map representations. What is right for the task? What are the interfaces between these different modules? And perhaps in relation to that also questions around, well, data efficiency, questions around uncertainty. Again, at the interface, you want to be somehow, you want to know how sure you are about the things that you're estimating. And finally, I think there's a lot to do in terms of human-robot interaction. How can we really now benefit from these advanced map-based concepts, and how can we interact between a robot and an operator in a meaningful way that really fully leverage these concepts that we introduced. Thank you very much, and hope I can take some questions also in the Q&A sessions. Thank you.
So I would like to thank the speaker. Now it's time for a Q&A session. So I would also ask the attendees of using the Q&A form of the Zoom room to ask questions if they have any. I think Stefan Leutenegger is already in the call, so I guess he's ready to take questions. I can already start with one question, if I may. So the question would be, where do you see the main challenges to make drone delivery or autonomous driving feasible, rather in improving perception and making it more robust, or in reliable path planning and decision making?
Hi, and thanks again for inviting me, being here. I'm trying to start the video. It didn't work before. Somehow it didn't seem to be enabled, but that doesn't really matter. So
I think it should work now, sorry.
Oh, okay, no worries. It's also not that important. All right. So yes. So what is more important? Well, I mean, I'm doing vision for robotics, so clearly I have to say that it's a perception problem. But I genuinely think that this is where the main challenges really are. I think in some sense, though, it's somewhat at the interface of the two, right? So depending on where you draw the line, you can push the problems into one side or the other. But I do think if we had really the right, the perfectly robust kind of map representation, spatial understanding, then the rest would kind of follow from there. The decision making would be straightforward, but it's almost impossible, I think, to actually get there. So I think that is in some sense the big challenge, that yeah, we can see this gap, and it's kind of it's closing, but it's still, we're still very far away from closing it perfectly, right? So yeah, I think to make it practically feasible, I think we will have to somewhat probably limit the scope a little bit, and we will have to limit the use case and perhaps what that exactly means, drone delivery or autonomous driving. Can we really do it in any environment, at any time, in any kind of condition, or do we maybe want to just slightly adapt, maybe have a little bit of, you know, special delivery points, some kind of markers in the drone case now for approaching in a safe way, maybe some requirements about how clear the approach path has to be, and things like that, that I see as a sort of more realistic engineering-based approach towards making it happen. Although, of course, ultimately, I would like to see it in this very general form delivered anywhere. But I do think we are really quite far away still from that.
Right. Thanks a lot for your comments on this. There would be one more question, which is, in most of your experiments, you are using depth cameras for 3D mapping. How far do you think we can go with monocular passive cameras in terms of accuracy and robustness? Do you believe they can replace active sensors? Yes,
that's a good point. I do think actually we can get there. And again, I think it is thanks to learning. I think that you know, we have even ways to do monocular-based depth estimation. Then, of course, if you combine it with the kind of visual inertial, actually metric trajectory reconstructions that we can already do, so then leveraging structure from motion, the kind of baseline through structure from motion as well. So a kind of combined learning and geometric model-based probabilistic fusion approach, if you will. I actually think this should be absolutely possible. It's computationally still somewhat heavy, depending though very much, I think, on what accuracy you really need, in map accuracy you really need. So again, I do think there's a lot of tasks that we can probably solve already now with onboard processing, where you don't need incredibly detailed 3D reconstruction, 3D maps. But I think we will make a lot of progress, and I do think that ultimately we don't necessarily have to rely on active cameras anymore. But they are just very practical at the moment. So I really like using them, because it really gets you going quite easily. They're available. You can just plug them in, and they work. And that's been good. But I do think there's a way forward to actually at some point overcome that limitation of having to have active cameras.
Yeah, I think that's a very good point. There's another question, as it's going in the direction of deep learning. To what extent do you think deep learning would be part of these systems? Are very deep models needed for parts that do not involve human labeled data?
I don't know. I'm probably not enough of an expert, or the question is maybe also deeper than you might think in some sense. I mean, there's a lot of progress that has been done in terms of self-supervised data. So I'm not sure it's so much a question of a lot of data that is needed from human annotations when it comes to just kind of geometric part of things. I actually think we are quite in a convenient situation. We can get away with self-supervised approaches a lot. Now, how deep these models have to be, that's I think that where I'm not sure, right? It's a matter of probably trial and error, how deep it really has to be. I mean, I still believe, though, that implicitly these models will have to learn something like semantics. And then, you know, you predict depth as a function of those learned semantics, where there's some form of scale associated with it. But because it's all implicit and doesn't require labels, it's very convenient in that sense, but probably will still need some level of depth. But yeah, I'm probably not in a position to give a very clear answer about that.
Mm-hmm. Yeah, thanks a lot for answering. There would be one more question regarding the optimization of your methods. So the question would be, in most of the optimizations, the convergency of several loss functions is a challenging task. Could you maybe elaborate a bit more on it? It's more like a general kind of question.
In the model predictive control part, yes. So, I mean, this is very clear. We are optimizing nonlinear cost functions, nonlinear least squares typically. So there's no guarantees of convergence about them. Now, in practice, they work really well, but it is, of course, true that if you wanted to certify these systems and really have certain guarantees around it, you would probably want to do more than this. I think a way around it can be that you start with a simple controller that you can kind of fall back onto, and that may also serve as an initialization condition. So in some sense, you will then always be at least as good as that kind of controller that comes with some guarantees. So it actually will give you those basic guarantees, but in practice, still a much better performance. So I think this is how I like to think about it. In this way, we can actually employ quite sophisticated concepts. And by the way, this can, you know, go as far as to, you know, have some deep learning parts in there where naturally we will really struggle with giving any guarantees and certification around it. But we can have some fallback solutions when we don't have to absolutely rely on these.
Okay, yeah. The next question would be, the current map representation mainly used in robotics, they are still dominant by the classical ones like 3D landmarks, point clouds, and voxel grids. Do you think they are already enough to support the sophisticated tasks like autonomous driving, delivery, and so on? And if not, what do you think would be the next step in this direction?
Yeah, again, I want to say I'm not really an expert on autonomous driving. So I do think that's a bit of the difficult part in this whole discussion, that really these map representations are, I think the best representations are very much coupled with the applications. So there's probably no one answer to that question in some way. It really depends what you want to do. So if you just simply want to not collide in a static environment, then I do think these approaches are very much sufficient with volumetric, maybe octree-based occupancy maps and so on. If you want to do much more sophisticated things, then we are arbitrarily far away, I think, from solving this. And this is also good news, of course, for us as researchers, that we still have a job to innovate. I'm quite interested in the kind of implicit representations as well, kind of learning codes and so on about different objects. I think one of the key questions is always what is the prior knowledge about the environment? To what degree can we use some form of model? It can be quite abstract models. It can still mean that there is still some form of a representation that needs to be optimized or estimated. But if you know a category of it being a car, for instance, then it probably doesn't make sense to go and fully reconstruct it from scratch, right? However, you may also not want to just look up the very specific model in a big database. So where do we go there in between? I think that's where still quite some research can be done. And of course, some of the other speakers have already touched on that. I mean, this is the key question, the question of representation, and what is the right representation for the task? And I don't think there is one answer to that.
Yes, thanks a lot for your extensive answers. I think it was quite interesting for all the attendees. If there are no more questions, I think I would hand over to the next speaker. So I would like to thank you very much for being here in the workshop and also for answering those questions.
Thanks,
so
pleasure.
Happy to have you here. And therefore I would introduce our next speaker, Raquel Urtasun. And Raquel is Uber ATG Chief Scientist and the head of Uber ATG Toronto. She is also an associate professor in the Department of Computer Science at the University of Toronto, which is a Canadian research chair in machine learning and computer vision and the co-founder of the Vector Institute for AI. Prior to this, she was an assistant professor at the Toyota Technological Institute at Chicago, an academic computer science institute affiliated with the University of Chicago. She was also a visiting professor at ETH Zurich during the spring semester of 2010. She received her bachelor's degree from University Pública de Navarra in 2000 and her PhD degree from the Computer Science Department of École Polytechnique Fédérale de Lausanne in 2006. She did a postdoc at MIT and UC Berkeley. She is world-leading expert in AI for self-driving cars, and her research interests include machine learning, computer vision, robotics, AI, and remote sensing. I'm very much looking forward to her talk.
Hi everyone, my name is Raquel Urtasun, and I'm the Chief Scientist at Uber ATG, as well as a professor at the University of Toronto. Today, I will be talking about localization for self-driving vehicles. Self-driving vehicles are one of the most complex and safety-critical modern-day applications of robotics. Leveraging rich maps can enhance performance and safety in areas such as perception, active prediction, and motion planning. In order to leverage these maps, the vehicle must know its position within them. This is the task of localization. Self-driving vehicles utilize high-definition maps, which contain both detailed geometry and semantic information about the environment. These are used for precise localization of the self-driving vehicle as prior knowledge for the autonomy system and for simulation. Self-driving companies are interested in creating globally consistent 3D maps of the world. In the industry, many passes over the same area are required for these maps to be complete. However, we would like to reduce this requirement as this is very expensive. Furthermore, maps typically require large amounts of memory to be stored, preventing them from being able to produce and use at scale. Finally, we would like the maps to only contain permanent elements that we will see every time we drive around the map area. Building geometric maps is typically a three-step process, where the data is first collected by a fleet of vehicles. Map building is typically done from multiple passes through the same area to ensure full coverage and to be robust to transient objects. Then the data is offloaded and the problem is decomposed into trajectory fitting of small chunks, which can be performed in parallel. This is then combined into a massive global optimization problem, which can be solved, for example, with graph slam techniques. The result is high-fidelity maps of our cities. In the video, you can see reconstructions using both LiDAR as well as cameras, which are very complementary sensors for this task. In the reconstruction I just showed, we have removed potentially dynamic objects, which are, for example, moving or parked cars, by exploiting a state-of-the-art semantic segmentation. This state-of-the-art technique is illustrated in the video here. Filtering these dynamic objects is important and results in much crisper maps. This is illustrated in green versus red in the video you just seen. HD maps contain also very rich semantic information. This includes the location of traffic lights, lanes, crosswalks, as well as the rules of traffic at each intersection and road segment. As illustrated here, these maps are extremely complex and a great prior for the autonomy system. These semantic layers are typically manually annotated with very little automation. A process extremely tedious, time-consuming, and expensive. If you are interested in knowing how to automate this process, check out our tutorial on self-driving. The goal of localization is to, given a sensor observation and a previewed map, infer the location of the car in the map. We focus explicitly on map-based localization, that is localization within prior maps, since this is necessary in order to leverage the HD maps described in the previous section, in order to achieve maximum safety. Formally, we wish to model the robot's belief over its state space, where for localization, the state space corresponds to the robot's pose in the world. We denote the pose of the current time by XT and the observations by Z, and M denotes the prior map. The Global Navigation Satellite System, GNSS, is a common source of input, which is often involved in computing initial pose estimates, which are then refined with other sensors such as cameras and LiDAR. Over the last 3 decades, cameras and LiDAR have been leveraged in a wide variety of localization algorithms, many of which will be discussed later. IMUs and wheel encoders are also leveraged as additional cues, as they provide information that is complementary to the observations from cameras and LiDARs. There is a wide range of representations which can be used for localization, in terms of localization maps. HD maps can be built and annotated with information such as lane boundaries, lane types, signs, etc. These kinds of maps can also be used for localization. 3D geometrical models can also be employed. These models can be represented as dense or sparse point clouds, surfers, or other kinds of 3D primitives. Topological maps are possibly non-metric graph-like representations, such as those found on OpenStreetMaps, OSM for short. They are typically much less detailed than the semantic maps described on the left. Finally, simple occupancy maps can also be used. They are often represented simply as a top-down view of the world. Such maps can also contain additional attributes, such as surface reflectance or color, and have the advantage of encoding rich information about the structure of the world, while also being easier to store than other representations. The main characteristics we would like from a self-localization system running at the scales are low cost, as we naturally want to map very large distances, the ability to localize in real time, high accuracy centimeter-level localization, and robustness, the capacity to handle and recover from failures. However, in order to achieve these goals, there are still several major challenges which we have to overcome. Localization systems must be robust to the presence of dynamic objects in the scene, as these are irrelevant for localization. Geometrically degenerate areas, areas which lack distinctive geometric cues, can also be problematic. These areas are challenging for geometric localizers since observations can't be uniquely aligned to the map. Sensor noise affects all sensors in different ways. Multipath effects can affect both GPS and LiDAR and cause difficulties localizing. Finally, environment changes such as construction mean that localizers must be able to adapt to cases where maps become updated. Now that we have gained some big picture context of what localization is trying to solve, it's time to dive into some of the mathematical foundations of probabilistic localization systems. There are two main parameterizations of vehicle pose using SDVs, short for self-driving vehicles. The minimal parameterization has just 3 degrees of freedom: the latitude, longitude, and the yaw of the vehicle with respect to the map. While very minimal, this representation makes sense for vehicles since they travel on the ground manifold, and the other 3 degrees of freedom, pitch, roll, and height, can be readily derived from the map. The full 6 degrees of freedom representation is more complete and fully describes the pose in the 3D world. It can lead to more robust state estimates, albeit at higher computational cost. It is also required in cases where the on-ground assumption no longer holds, as is the case, for example, in flying cars. Note that we do not only care about a point estimate of the localization, but also a confidence measure over the space. The probabilistic framework allows modeling of uncertainty as well as tracking multiple pose hypotheses and recovering from failures. We have thus established the benefits of modeling a probability distribution over the state space, rather than a point estimate: uncertainty modeling, multi-hypothesis tracking, and recovery from failure, to name the main ones. In this context, we can look at localization as a probabilistic inference problem, that is, estimating the belief over our state space, which in this case happens to be a position. Mathematically, we denote our states at time t as xt, and our observations, which can be LiDAR, IMU, or GPS, using z. We operate under the Markov assumption, where the belief over our state at time t-1 encodes all the information from the past states, allowing us to predict where we will be at time t. We will see why this is a good idea once we have a look at how this estimation is implemented in practice in the next few slides. Note that we restrict our scope to the case of online localization, which assumes a good initialization is always available to solve the problem. We will discuss global localization and system initialization later in the talk. Focusing on discretized temporal dimensions, for example, at 30 Hz, use localization as a recursive Bayesian filter, which can be solved with a simple yet effective algorithm. So right now, I'm going to give a very brief overview of how the Bayesian filtering framework works in the context of localization, but it's worth pointing out that this is a very general framework that is in no way restricted to the task of localization. There are essentially 2 main steps in the algorithm that keep getting repeated over and over as a robot moves through an environment. These are prediction and observation. Each iteration begins with the prediction step. This step uses a propagation model to compute a prior belief over the current state based on the previous state posterior. For localization, this propagation model can be given by a kinematic model, for instance. Since I was here 0.1 seconds ago and my velocity is this is where I will likely be around, assuming if I assume constant velocity. The rightmost term in the last step's belief is the last step's belief, while the middle one highlighted in magenta represents the propagation model built into our system. The second step updates the prediction from the past step based on the current observation. This is what integrates new observations from our sensors into our belief. On the right, we see an illustration of a Bayesian filtering procedure. The state space is unidimensional. It's just a scalar depending on the robot's position in the corridor. The robot on top begins with no idea where it is. The belief over the state space corresponds to a uniform distribution. Then, in the second row, the robot performs its first observed step and notices that is near a door. However, the pose is ambiguous since it cannot tell which door it is. The robot then moves, applying its transition model to approximately propagate its old belief based on how it moves. This represents the first step of the second iteration. This increases its uncertainty, as denoted by the widening peaks, as directive motion readings are typically noisy. Finally, in the second step of the second iteration, the robot observes another door and fuses this information with its current belief. This additional information helps disambiguate the robot's pose, allowing it to converge to a mostly unimodal distribution over its location. Note that this example is purely conceptual, since in practice we cannot solve the integral in closed form. Proper Bayesian filtering results in an integral over the state space at the previous time step that is oftentimes intractable. So there are a number of common approximations used to tackle the problem in practice. For example, we can assume that the distribution is unimodal, transitions are linear, and both the noise of the beliefs are Gaussian. This results in a Kalman filter. We can also approximate the integral via Monte Carlo sampling. This is known as particle filter or important sampler. The third alternative is to discretize the distribution, which results in a histogram filter, which is easier to work with, but can be computationally expensive. So to recap, we can elegantly model recursive Bayesian estimation using a pure mathematical form. In practice, we have to make some trade-offs in order to implement this in a real robot. A Kalman filter is able to produce convenient continuous closed-form estimates, but it is limited in its modeling power. Its unimodal nature means that it is unable to track multiple hypotheses. Particle filters can bypass some of these issues and approximate the quantities by sampling. However, the modes of the distribution can still collapse as the number of particles necessary to model the distribution grows as an exponential function of the number of dimensions of your state space, which can be quite large. Histogram filters can also represent arbitrary system models and arbitrary noise models without risking any sort of collapse, albeit at a much higher computational budget and with limited resolution. However, later on this talk, we will see how we can still leverage the best parts of histogram filters without a large computational cost. A common element in non-localization efforts is the need to always integrate new observations. Observations can take in a wide range of forms, ranging from direct census readings like the IMU, all the way to a neural network that perceives the 3D scene from sensor readings. Let's look at different observation models. Real-time kinematic systems leverage differential GPS and inertial measurement units to estimate vehicle trajectories. Semantic matching tries to match cues extracted from sensor observations to maps which encode the prior locations of such cues. Geometric alignment infers the vehicle pose by rigidly aligning the perceived geometry to a known 3D map. Camera-to-LiDAR matching aims to leverage inexpensive cameras to localize against maps built from more expensive LiDAR, either using heuristics or learned feature matching. Glitch recognition has localization as an image or LiDAR retrieval task. Localization then consists in mapping the sensor readings to a previously seen and localized one via nearest neighbor search. Finally, LiDAR reflectance matching compares the LiDAR intensity readings to the map at multiple candidate locations in order to find the correct pose. In principle, any of these approaches can work with any of the previously discussed frameworks. You can do semantic matchings via a Kalman filter, a particle filter, or a histogram filter. You can filter GPS using particle filters, etc. I'm now gonna highlight a few observation models with some of the work that the lab have done in the past few years. Let's look at semantic matching. This approach leverages compact maps of a few kilobytes per kilometer, storing only semantic cues like lanes, signs, turns, and road type. all of which can be stored as vector maps. At runtime, the car must recognize these elements and match them against the vector map to localize. Unfortunately, due to the sparsity of the queues, these approaches cannot achieve centimeter level accuracy and struggle in areas where the detection is challenging. Examples of these approaches include Lost, which require an OSM or OpenStreetMap vector map, and our recent work which exploits lanes and signs for localizing on highways, which can actually automatically create these HD maps and then localize to them. Geometric alignment methods rely on aligning 3D sensor data to pre-build 3D HD maps. These methods can be very accurate, relying on well-established, conceptually simple methods that can be robust to outliers, such as the iterative closest point algorithm. The downside is that these methods require a good initialization for convergence, as registration is prone to local optima. Additionally, storing and building 3D geometric maps can be challenging and expensive. Despite these drawbacks, these approaches are very popular in the self-driving industry, probably the most popular across all of them. Lidar reflector matching. This approach builds a map using lidar intensity imagery and matches online observations from the 2D image using simple template matching operations such as cross-correlation. These methods can be much more robust than geometric ones, especially in mostly featureless environments. For example, if you're in the middle of the desert. The template matching itself can also be implemented in a very computationally efficient manner and achieve centimeter level accuracy. At the same time, just like the geometric alignment methods, reflectance matching methods require good initialization. They also have relatively high map storage costs. Through the 2.5D maps used by these approaches are typically much easier to compress than 3D ones, as we will soon see. These methods also require very precise lidar intensity calibration, which can limit their scalability due to the difficult nature of this procedure. As when you are working in the self-driving industry, you need to have the same map for a fleet of vehicles. Potentially, these vehicles might not have exactly the same calibration settings. Finally, these methods are typically limited to estimating only 3 degrees of freedom, being unable to directly infer the height of the vehicle. However, as discussed previously, the height, pitch, and roll of the vehicle can be inferred from the map, yielding a good solution. Despite these drawbacks, many self-driving companies exploit localization systems based on lidar intensity matching. Our recent work has addressed the need for intensity calibration by learning a deep invariant mapping for matching in an end-to-end manner. First, we pass the online lidar sweep and the map through separate, fully convolutional networks to compute corresponding embeddings. Following the histogram filtering framework, we then compute a matching score for every pose within a limited search range of our dead reckoning pose. The search range is over X, Y, and heading, so 3 degrees of freedom. This matching can be performed very efficiently in the Fourier domain with the specialized Goodell kernels, yielding localization times that are real time. The matching therefore yields a 3D score volume, which corresponds to the observation probability in the projection filtering framework that we have reviewed before. This motivates us to go one step further. We incorporate a neural network compression model within this network. To encode the input map to a compact binary code. Importantly, we only need to store the binary code on the car. The compression model is highlighted with the gray box. This compression model is made end-to-end learnable. In other words, learning will decide what information it will keep and what to discard. Unlike prior compression work, it directly optimizes the trade-off between compression and localization accuracy, as opposed to the trade-off between compression and distortion commonly used in the general purpose compression literature. So overall, in this work, we use learning to get robust and compact feature representations. And we use model-based knowledge to formulate the problem and integrate prior into the variation filter. This is just a technique that is extremely robust to any calibration issues, and I can achieve 3 centimeter error with millions of miles. As a result, We have reduced storage by 3 orders of magnitude with only a slight accuracy drop. And importantly, our approach is much more storage efficient and accurate than storing maps using standard lossy compression algorithms. Based on our computation, this compression allows us storing a centimeter accurate localization map for the entire high-definition US road network in a single commodity hard drive. By combining machine learning with human knowledge of the world, we have made localization more scalable. The take-home message is that when designing data compression algorithms for robotic applications, we should exploit the fact that consumers are robots instead of humans, and our goal is to preserve downstream task performance. Here we show some qualitative results. On the left is our online LiDAR. In the middle is the map, and on the right is the localization result. Vehicle pose predicted by our method is in red, and ground truth is in green. Note that in these cases, we can see that our pose and ground truth pose are almost perfectly aligned. I will now talk about a different topic, which is global localization. The method that we have seen so far have been focused on online localization. The natural question is, how do we obtain our initial pose? And how do we recover when Bayesian filtering method fails? This task is known as global localization. The challenges here are, for example, that the same place can look very different due to factors such as weather, time of the day, season, dynamic objects, and so on and so forth. Another challenge is that obtaining good large-scale training data for this task remains difficult. There are two main approaches for this problem, post-regression and retrieval-based localization. Post-regression takes images or LiDAR point clouds as input and directly outputs the pose for the car. This method is extremely fast, yet there is a lot of evidence that these methods do not achieve good accuracy at city scale. Retrieval-based methods, on the other hand, are slightly slower and have potentially large memory requirements because they have to store the entire observation dataset, but tend to be much more accurate in large geographic scales. We have investigated the retrieval approaches in the context of self-driving and designed a large-scale dataset and benchmark for this task.
We introduced PID30M, a dataset for large-scale localization tailored for self-driving applications. For scalable localization in a city setting, we would like a dataset to 1. Be diverse, 2. Cover an entire city, 3. Provide accurate localization ground truth. Our dataset satisfies these 3 criteria and does so at an unprecedented temporal and geographical scale. Our dataset includes images and LiDAR point clouds, each localized with accurate 6 degrees of freedom poses. We also carry a consumer-grade GPS sensor, which we can use to bootstrap localization. Our dataset also provides a set of labels that allow researchers to better understand the limitations of current localization algorithms. For example, we provide sun angle, season, temperature, precipitation, and semantic segmentation as a proxy for occlusion. With over 25,000 kilometers driven, 30 million images and LiDAR readings, and an area of 50 square kilometers collected over 1,300 trips, our dataset is between 10 and 100 times larger than previous datasets released to the community. PID30M provides a challenging benchmark for large-scale localization, particularly suited to autonomous driving. We plan to create an evaluation server for automatic benchmarking and for keeping track of the progress by the community. We hope that our dataset will help researchers develop new and exciting algorithms for this task.
We also did an in-depth benchmarking, comparing multiple approaches in our dataset. The main takeaway point from our experiments is that the strong architectures with simple pooling schemes show excellent performance in this task. In this plot, the x-axis goes from 0 to 1 meter, and the plot indicates what % of the queries are correctly localized within a certain distance. As you can see, GPS struggles to localize even 5% of the images within a meter, which is not good enough for autonomous driving. We benchmarked baselines that are commonly used in previous work, including MLAD, NetMLAD, and LensMLAD. And we noticed that they only localize about 50% of the queries within 1 meter. These methods rely on broad pooling, which has established itself as a strong baseline for many retrieval tasks. However, training a ResNet 50 with average pooling performs very well on this task, returning over 90% of the queries within 1 meter and over 70% within half a meter. Another thing that we can do is, instead of searching for nearest neighbor in the entire database, use GPS as initialization and then search only within an area of, for example, 20 meters around it. This consistently improves results for all methods and improves also our ResNet as well. The previous results were all using images only, but we can do a very similar experiment with LiDAR. Obviously, the performance of GPS is the same. The methods that we benchmark here are PointNet with max pooling, PCAN, and PointNet MLAD. These methods all process points individually, like PointNet, and rely on complex aggregation schemes at multiple levels. In contrast, we represent LiDAR in VersaView with a VersaView representation, which we also use for perception and prediction in our vehicles, and are thus able to treat the point cloud as an image, which we pass through a ResNet 50 with average pooling. We have found that this consistently outperforms other methods as well. We can also use GPS for initialization, which helps most methods. It is curious, however, that GPS can slightly hurt LiDAR retrieval on short distances. This is because sometimes GPS can be off by more than 20 meters, so that retrieval methods initialized with LiDAR cannot recover from bad GPS in that case. Here are some qualitative results of our method. Note that on the left, we show the query, and the first 3 results are retrieved using the image. The last 3 results are retrieved using LiDAR. In this particular example, we see that the image retrieval network finds the same place only 61 centimeters away, but under snow conditions. This means that the network has learned to be invariant to the weather in the scene. LiDAR also finds the same place, but does so with only 17 centimeters error. In this other example, we see the image network retrieving the same place at night. Methods such as MLAD, and DenseMLAD find images that look similar but correspond to a different place. Once again, LiDAR is consistently more accurate. The final example is a query that does not have a lot of distinguishable visual features for the network to latch onto. Nevertheless, the network can retrieve the same place by finding the same building. Again, LiDAR does a better job, finding an example that is only 12 centimeters away. Some remaining challenges in global localization include using both images and LiDAR. In the example that we described, the networks use only the network only uses images and LiDAR, and we found that fusing information from both is actually really non-trivial. Exploring for generalization of these methods to multiple cities also remains underexplored. For example, we would like to train on a city on the East Coast and be able to generalize to cities on the West Coast, or even across continents. We would also like to explore systems that do both global and continuous localization. Training these 2 things together remains challenging. Finally, state-of-the-art large-scale systems for approximate nearest neighbor search rely on data structures that are themselves learned. So jointly learning to localize globally and efficiently find nearest neighbors will be an interesting area of research as well. So to recap, we have first described localization with prebuilt maps. Then we introduced Bayesian filtering for continuous localization. Here we discussed Kalman filters, particle filters, and histogram filters. We then gave an overview of methods for map-based localization, and finally we discussed global localization and its challenges. Important future directions include reducing our reliance on high-definition maps, as these remain expensive to build and hard to get right. Finally, Bayesian filtering typically discretizes time. However, in real-life sensor inputs come continuously, and they are typically at different frame rates, each one of these sensors. So designing methods that explore this fact remains challenging and very interesting. Finally, since we are interested in self-driving, we have to remember that we have limited computational resources on board. So designing systems that can reuse computation to do localization and other tasks such as perception, prediction will be a very interesting idea. Thanks for your attention. This is all from me. Thank you.
So I would like to thank the speaker for the great talk. Again, now it's time for a Q&A session. I would also, it's my pleasure to welcome Raquel Urtasun for the Q&A session. If I may ask, I can already start with one question. So I would have a question regarding the HD maps. So in the talk, you have been mentioning a lot of different properties of HD maps. What I would be interested in, what should be the key components of an HD map, and for which task do we need which information?
Sure. So thanks for the question, Patrick. I don't seem to be able to put my video. I think you guys are controlling that. I don't know whether, I think it would be maybe better for the audience. Cool, fantastic, great. So let's see. So HD maps. So the I guess there is typically like two layers in HD maps. There is the geometry as well as the semantics. And the geometry typically is, in the form of, say, 3D point clouds, and this is exploited for localization itself. There's a lot of like ICP-based localizers that you typically see in self-driving cars. And also the geometry is useful for things like perception, where in order to limit your computation, for example, knowing where the ground is also very important. And typically, right, we've seen a lot of assumptions in papers about the ground planes, but in reality, a ground plane assumption is actually pretty off in many different scenarios. For example, say San Francisco with hills. The semantics, we see less of semantic-based localization in terms of real systems, but there's a couple of options there as well, and those are exploited definitely for motion planning, right? Where you really need to satisfy all the rules of traffic, etc. And also you see their use more and more in modern perception and motion forecasting systems. For example, for perception, knowing where the lanes are gives you a very good prior into orientation of the vehicles, also into their motion. Also knowing the state of the traffic lights is going to also give you a lot of information. Now, one of the things that is important also to know is that these are priors, and it's very important that your system is not overconfident on those priors, meaning that there is a lot of illegal maneuvers and things that you will not expect that actually happen in practice all the time. But basically, they are used throughout the whole stack.
All right, thanks a lot for clarifying. I would have a slightly following up question on this topic, basically. So we're also mentioning about how to store and resources pre-built maps, basically, and how to store them efficiently. What I would be interested in, if you store them efficiently and you also compress them, how do you deal with updating them? Because actually the environment is changing all the time out there. And if you compress them, so how can you keep them up to date efficiently?
Yeah. So I guess the up to date is regardless of compression. I think is a topic in itself, right? In our case, typically, there is a lot of elements that we listen online, things like construction, etc., where you need to make sure that you immediately update where these elements are within your memory or your map, right? Now, for other types of changes, like for example, where you're supposed to stop at the intersection is suddenly different. Typically, that doesn't change so often, right? So there is two things that you can do, right? You can do it through live updates, right? Or you can do it through also particular vehicles that are scouts and look at the environment. So the latency of how quickly you can and how much evidence you need might differ depending on which approach you actually have. Now, in terms of compression, it's one of my favorite topics. We're doing a lot of compression these days in the lab. Let's see. So I show one particular localizer that with intensity maps, which works extremely well, and you can compress extremely, a lot, such that you can actually fit, the whole North America in the vehicle. So that's a case where you want to do this compression prior to start driving. There is other types of compression that you can use as well for, say, geometry maps. And for example, we have a CVPR paper on learning to compress LiDAR point clouds. So that's actually very useful in that case as well. But in general, it's also interesting a line of research that we've seen a little bit on images, which is, do you even need to decompress stuff in order to do inference, right? So I think that's also very interesting in the sense that every computation adds up in the vehicle, right? So you need to make sure that, you know, localization should be a very, very tiny process compared to, say, perception, prediction, motion planning. And in terms of I guess updates, so you can always update and you know, compress back and send, right? So the fact that it's compressed allows you to send back from, say, your centralized system to the vehicle, so that doesn't necessarily hurt it. Yeah. And
Okay,
I guess
thanks.
in the case of retrieval, right, is easy to just update your bank of images or LiDAR points.
Okay, great. Thanks a lot. Maybe the final question. You have been talking about permanent elements of a map. So how do you determine which elements are permanent or basically static in the map and which are changing?
Yeah.
For example, if you have to deal with construction zones, they may be permanent for some time of the year, but they don't necessarily need to be permanent for, let's say, 2 years, right? So this is also like a tricky question. Maybe you can comment on that.
Sure. So, I mean, typically in the production system, so what we, what we do is that we use, say, semantic understanding, right? Things like semantic segmentation of point clouds in order to understand what are the points that actually we expect them to continue versus not, right? In the case of construction, for us, we treat construction as non-permanent. And the reason why is, there is so many things that move in a construction site that you better, you can mark things like there is a construction site, but the actual shape is going to vary anyways. So that's one that you definitely want to make sure that you have a lot of inference, online inference into what's happening over there.
All right, thanks a lot for your time and answering those questions. I'm again happy to have you here for the Q&A session. So I would like to thank you again.
Here. Yeah.
So with this, I would like to conclude this talk and thank you again, and would move on to the next session. Thanks a lot. So now we would continue with the relocalization challenges, and we would start with our first speaker, Paul-Eduard Salin from ETH Zurich, the winner of our relocalization challenge. And I'm happy to play back his talk.
Hi, everyone. My name is Paul-Eduard Salin, and I am a PhD student at ETH Zurich in the Computer Vision and Geometry Lab. I am here to talk about hierarchical localization with our toolbox HLOC and Superglue, which won the first place of this challenge. Our submission builds on top of 2 of my past works. HLOC is a toolbox for visual localization that was open sourced last month. It was developed at ETH Zurich with the support of Mihai Dusmanu, Victor Larsson, and Prof. Mark Polyphase. HLOC is integrated with Superglue, a graph neural network for feature matching. I developed Superglue when I was at Magic Leap in collaboration with Daniel Detone, Tomasz Maliziewicz, and Andrew Rabinovich. HLOC and Superglue reached the first place in 6 localization challenges. 2 of them were at CVPR 2020 last June and were about local features and handheld devices. This week at ECCV, we won 4 challenges. One is organized by this workshop on map-based localization for autonomous driving and will be the focus of this talk. We also won all 3 challenges of a workshop on long-term visual localization under changing conditions, and I will give one talk over there on Friday. Our general idea is based on hierarchical localization, introduced in our CVPR 2019 paper. For a general localization problem, we can use deep learning for both image retrieval and matching by predicting global descriptors and local features. We do this for both database and query images, and we build a structure from motion model for the database. For a query, we retrieve some relevant database images, cluster them based on the co-visibility, and match their local features. Finally, we estimate a pose from the resulting 2D-3D matches. At the core of our current solution lies Superglue. It is a graph neural network that estimates matches between local features in two images, while rejecting unmatched points. Superglue combines deep learning and optimal transport, and can successfully match image pairs with extreme baseline in real time. This results in state-of-the-art pose estimation with both classical and learned local features. We presented Superglue at CVPR last June and demonstrated great generalization for both outdoor and indoor localization. You can find the paper, the open source code, and the recordings of our CVPR talks at psarlin.com/superglue. Complementing Superglue is HLOC, a toolbox for structure from motion and localization. From a set of images, it can reconstruct a sparse 3D model using any local features. Then, it can localize a given query image into the 3D model by estimating a 6 degree of freedom pose. Let's look at the task of 3D reconstruction. Given a set of images, we first extract some local features, which are then matched across images. These matches are used for structure from motion, for which we use the incremental mapper in CallMap. We, however, need to decide which image pairs to match. We can use all image pairs, which is called exhaustive matching, but is slow. We can also restrict the matching to images that are visually similar, using image retrieval. If we have GPS information, we can also match only images that are spatially close. Of course, all of this is already implemented into CallMap, so why do we bother adding another layer on top of it? Well, CallMap only supports SIFT, while HLOC supports several recent deep learning-based local features, like SuperPoint or D2Net. It also supports several matchers like Superglue. And since all of this is implemented in pure Python, it's extremely easy to add new local features or new matchers. If we are given prior camera poses and a 3D model, for example from LiDAR alignment or SLAM, we can also generate image pairs using co-visibility and triangulate a new model using our favorite local features and matcher. Finally, we can localize a new query image by extracting its features, matching them, and lifting the 2D matches to 3D using the 3D model. The pose is estimating with PNP plus RANSAC. The image pairs can be selected by image retrieval, and we obtain our hierarchical localization framework from coarse image retrieval to find local features. HLOC can also localize multi-camera rigs using a generalized PNP solver, which is very useful when localizing robots or headsets. HLOC can work with several datasets from visuallocalization.net. For outdoor environments, we build structure from motion models, as described previously, for Aachen Day Night, Robot Car Seasons, CMU Seasons, or SILDA. Some of these have multi-camera rigs, for which we will release tools soon. For indoor environments, it is also possible to use 3D LiDAR scans, such as for the InLoc dataset. Let's now look at the Re-Localization challenge. This is a very basic application of our pipeline. We first use the reference sequence and its camera poses to triangulate a sparse reference 3D model. We use SuperPoint features and match the 20 closest images with Superglue. We then localize each test image independently by matching it to the given reference image and its 20 nearest neighbors. Let's now look at the results. The localization accuracy is evaluated on 2 test sequences as 3 distance thresholds, 10, 20, and 50 centimeters. We first have 4 baselines. There's large room for improvement, and superglue, the last baseline in orange, doesn't seem to perform that well. Here's a second place in green. It's a bit better. And here in red is our solution. That's a big difference. On the first sequence, more than 90% accuracy at all thresholds. 99 localization within half a meter. 4 to 5 times better than all other approaches at the fine threshold. But what's particularly striking is a difference with the public superglue baseline. What is going on there? Let's look at the pipeline used for the baselines. We first extract features from query and reference images. Okay, that's fine. 2D to 2D matching with nearest neighbor or superglue. That is the same as in HLOC. Next, compute a disparity map for the reference stereo pair with OpenCV stereo matcher. Okay. Then lift the reference 2D key points to 3D by interpolating the disparity map. And finally, pose estimation from these 2D to 3D matches. This doesn't look very standard. Let's look at the kind of disparity produced by this OpenCV stereo matcher. This is from the Kitty Stereo 2015 benchmark, which looks very similar to the sequences given for the challenge. It's very noisy. There are a lot of artifacts and pixels with invalid values. This is another example, same conclusion. It's really not the kind of high accuracy needed for absolute pose estimation. The steps 3 and 4 give very inaccurate 3D points, which results in a catastrophic performance of the baselines. Differently, in HLOC, the 3D points are estimated with triangulation and bundle adjustment, which is the proper way of doing it. This raises some concerns. How is the GNNet paper evaluate superpoint and D2net? I don't know, but if this is the same, then it doesn't seem fair. In any case, I recommend everybody to evaluate local features with HLOC because it works the best. It is also interesting to think about future research directions. Where can we improve the performance? What should researchers work on? This is my personal list. First, we should strive to go beyond 2D key points. How to combine the robustness of key point-based localization with the accuracy of direct image alignment. How to do so in an efficient and scalable manner. I think that GNNet is an interesting direction to address this. Next, image retrieval. For this challenge, we were given localization priors, but in the general case, we don't have them. Image retrieval is often the bottleneck, so how do we improve it? Is it just about having more data? Lastly, we should try to better leverage sequential information. For now, we are localizing single queries. But what is the best approach to localize sequences and leverage their structure? I believe that HLOC provides a good framework to integrate all these improvements and evaluate their impact. To conclude, I presented our localization pipeline based on superglue and HLOC, which is a simple and clean toolbox for visual localization. You can do a number of very exciting things with it, For example, obtaining state-of-the-art localization accuracy on a number of public benchmarks. Maybe you can even win the next competitions with it. You can also localize with datasets that you have collected yourself by running structure from motion with superglue. Of course, for your next paper on local features or image retrieval, you can evaluate on localization with HLOC within a few minutes of setup. Perfect for stressful conference deadlines. And lastly, you can experiment with new localization pipelines and easily debug them. All of this is open source, pure Python, with already several community contributions. Do check it out. I am Paul Edward Sarlin, and this was my presentation about superglue and HLOC for visual localization. You can find our toolbox as well as the corresponding publications following this link on GitHub. Please feel free to open an issue if you encounter a bug or would like to request new features. You can also reach out to me on Twitter or by email. Lastly, you can join my second ECCV talk on Friday, where I will cover our winning results on 3 other localization challenges. Thank you for your attention.
So thanks to speaker. I might comment on the baselines. Actually, the idea of the baselines was only to provide the most simple, accessible way in order to see how we can use our data. However, thanks a lot for publishing HLOC as a tool, and we are happy to also see that other researchers can work on our dataset with this amazing toolbox. But just to clarify, the baselines is just a way to access our data and how it can be loaded, basically. But thanks a lot for pointing out. But I can ask a related question. What do you believe if we skip the depth estimation step and we run pure 2D to 2D pose estimation? Do you think it would perform better?
So yeah, first, thanks for clarifying that. Super nice, and also thanks for inviting me to speak here. It's a great opportunity. So regarding your question, I think that it really depends on how you actually estimate the depth. So if we can use structure for motion and retensitivity of a matching, then it's possible to actually estimate the depth of a key point based really on a lot of different frames over the full trajectory, if a 3D point is actually covisible. So I think that if we have good constraints on the depth of the point, then we can get fairly accurate depth even with, let's say, key point based methods, you know, despite the noise in the 2D key points. Then whether it's actually possible to do that with just 2D to 2D image alignment, I think that's, right now, there's no real approach that would allow that on a competitive accuracy. Personally, my experience is that two-view geometry estimation from just 2D information is pretty noisy and very difficult and has a lot of degeneracies. So it's maybe a way to include more deep learning in the estimation of a pose, because I think that it will be better to work with only 2D information with deep learning. But I don't know if for more standard, let's say classical geometry pipelines, I don't know if that would be a very sensible decision. But that would be great to see more work done on that, I think.
Right, great. I would have maybe one following up question regarding your sparse reference 3D models, which you built with your HLOC toolbox and CallMap. And maybe you can comment on like what is the basically a limitation or like a practical limitation on how many images or like a large city scale, like how large scale you can go and still can obtain a suitable 3D model, and what is like the runtime?
Yes. Well, in this case, I think the maps are fairly small. We have a few thousand images, so the reconstruction was pretty fast, and it doesn't take much memory. The question is indeed how do we go on a larger scale? And I think that depends on a lot of things. First, how many 3D points do we actually need to localize? And associated with that, how many keyframes do we have? Do we have sparsely sampled keyframes, or do we have a continuous stream of images? of course, makes a difference. And I think that in the future, with more efficient localization algorithms, we can actually have smaller maps. And that's something that we have observed with Superglue, where if we have a strong method for feature matching, then we can work with much larger baselines. And that means that we actually need only a handful of keyframes to actually reconstruct the 3D information accurately. Whereas with maybe weaker features, then we need a much higher frame rate, and maybe we have more points, and the reconstruction also takes a lot more time. So I would say that now with deep learning, we can actually be able to localize with much smaller maps, and that's good news for the future, I think.
All right, so thanks a lot on your view on this point. If there are no more questions, I would thank you for the talk again, and congratulations again for winning the first place.
Thanks a lot for organizing that. It was really a lot of fun, and I appreciate you organizing this. That was great.
Great, thanks a lot for the feedback, and yeah, wish you a nice conference.
Thanks.
So with this, we would continue with our second place, Yaroslav Melikov. I'm happy to play back his recording as well.
Hi everyone, my name is Yaroslav Melikov. I'm a postdoctoral researcher at Aalto University, and I will now present the runner-up entry to the MLAD challenge, based on our technical report titled Image Stylization for Robust Features. This work was carried out at Niantic Labs, where I did an internship last year. I'm very thankful to my collaborators and mentors, Gabriel Brostow, Juho Kanola, and Daniyar Turmuhamedov, for their support and guidance during the whole project. In the next 15 minutes, I'll briefly talk about the problem of visual localization and the problem of estimation relative camera pose in particular. Then, we will discuss the challenges the localization datasets exhibit and how we can use photorealistic image stylization techniques to learn local key point detectors and descriptors to overcome some of these challenges. I'll present the achieved results obtained by our method, and finally, I'll conclude the talk by some observations we did during the work on this project. Let's first look at the typical two-view matching pipeline. First, key points are detected in each image independently, and corresponding descriptors are extracted. This can be done either with classical methods such as SIFT or learned approaches like Superpoint, D2Net, or R2D2. Then, the features are matched by nearest neighbor matcher, looking up the closest neighbor for each key point in the feature space. Since the nearest neighbor matcher is not very accurate and prone to outliers, the list of tentative correspondences is refined at the outlier filtering stage by applying some heuristics such as ratio test or mutual check, or using learned outlier rejection techniques. And finally, the relative poses are produced by a robust estimator such as RANZAC. For this competition, we kept the later part of the localization pipeline intact and used the source code provided by the organizers. This work is focusing on improving the quality of local detector and descriptor. In this project, we experimented with R2D2 model as the backbone network. However, the presented method can be applied to any learned key point detector and descriptor. All existing datasets for image-based localization are quite challenging, consisting of images taken at different illumination, day-night, weather, snow, rain, and lighting conditions, such as direct light. Our goal is to learn local key point detector and descriptor, which will be robust to different weather and lighting conditions. However, learning features that are invariant to illumination or weather changes is challenging, as suitable data is not easy to acquire. In our work, we show that color augmentations at training time increases robustness to appearance changes, but it is not sufficient by itself. Ideally, the training data should consist of static scenes, without moving objects or occlusions, captured under various illumination, weather, and season changes. One of the possible solutions is structure from motion data. Structure from motion systems can build 3D models from internet images that are captured at different times and weather conditions. Hence, training on this data introduces some robustness to appearance variations. However, building 3D models from images taken under such extreme changes is much more difficult. Another data source for appearance robustness is webcam footage archives, where stationary cameras throughout the world broadcast imagery for many years. One of the examples of such archives is the AMOS dataset. The AMOS dataset is a constantly growing publicly available dataset represents outdoor scenes captured by static cameras which store images in all seasons and during the whole day. However, this dataset has its own limitations, such as the fact that the scenes are not completely static. There are moving objects in the frames which are difficult to detect. Or the cameras have technical issues like bad focus or limited dynamic range. In order to learn a robust local image descriptor to illumination changes and avoid the limitations of the AMOS dataset, Milan Pultar post-processed the original dataset by removing images displaying highly dynamic scenes, like sky, blurry images, and also scenes which are not completely static. This filtering process was done in a semi-automatic way. As a result, there is a dataset representing static 27 scenes, 50 images per scene, captured at different weather and lighting conditions. However, the filtering process is not perfect, as we can see from the example below, where the right image has a van and a crane in the right, but the left image doesn't have these objects. Thus, this dataset can't be used as it is to learn a local key point detector and descriptor. In this work, we consider 6 different styles or categories: cloudy weather, dusk, mist, night, rain, and snow. We use the subset of AMOS dataset produced by Pultar and manually sample 10 images for each style. The sampled images have been post-processed by removing timestamps and watermarks. Some of the examples for each style are illustrated in this slide. As I mentioned earlier, for each style, we sampled 10 images with different appearance. For example, the night style has these style examples. This allows us to generate multiple stylizations for the same image, meaning that the single day image can be stylized using 10 different night images as target style, resulting in 10 night images with the same content and viewpoint. We use the photophorism dataset to train local key point detector and descriptor. In particular, from each training scene of the dataset, we randomly sample 300 images, and for each image, we generate its 60 stylized versions, 10 images for each of 6 categories. For image stylization, we use the method by NVIDIA as it preserves ages and objects after stylization, and like other methods designed for artistic style transfer, such as GANs. We trained feature networks using original and stylized image pairs. Crops are extracted from the original and stylized images using random homographies. So we do not use 3D geometry, such as depths, to establish correspondences between 2 crops. Image stylization and synthetic homography augmentation together allow us to learn features that are robust to appearance and viewpoint changes. During training, we optimized the objective function proposed in the original R2D2 paper. The network was trained for 70 epochs with warm-up and exponentially decaying learning rate. The goal of the challenge is to estimate the 6 degrees of freedom relative pose between individual images from a reference sequence to a test sequence. Some examples of the test data are illustrated below. The dataset consists of grayscale images captured in the morning, the reference sequence, and in the evening, both test sequences. For the challenge, only the translation accuracy has been evaluated. The relocalization results for both test sequences are provided in this table. The results are reported at the percentage of relocalization candidates which were localized within the given translational thresholds. The proposed approach could achieve promising results. Notice how additional stylization augmentation during training leads to a noticeable improvement in localization scores compared to the original R2D2 model. Interestingly, our approach could achieve good scores given the fact that the images of the test data are grayscale, showing good generalization performance of the method. In this work, we investigate if image stylization can improve robustness of local features to illumination, season, and weather changes. The proposed approach, trained on only synthetic homographies, could achieve competitive results in visual localization benchmarks, outperforming baseline methods. We also experimented with one of the learned outlier rejection approaches, such as Degenzag. However, we could not get any improvement and think we need to spend more time to investigate this behavior. The technical report is available online. Pre-trained models, as well as the dataset with stylized images, will be released soon. Our approach takes second place in 2 image-based localization challenges. The first one is the map-based localization for autonomous driving challenge, it was a topic of this talk. And another is the local features for day-night matching challenge, which is specifically carried out by a workshop on long-term visual localization under challenging conditions, which will take place next Friday, August 28th. We will present more results obtained by our method at that workshop. Please consider participating in this workshop too. Thank you for listening. If you have any questions, feel free to drop me a message. Thank you.
All right. I would like to thank the speaker. I would have the question, since we have been provided a few sequences, did you also consider actually training your models on the data we have provided?
Hello, thanks for the question. Actually not. So we just used one model which was trained on the phototourism dataset with these stylized images, with stylized augmentations, but we didn't use the training data provided by the organizers. So it's like one model evaluated on different test datasets on different challenges.
All right, thanks a lot. Do you see any benefit of leveraging the provided data, or do you believe the scale or the size of the data set is too small to train our own model?
Yeah, that's a good question. I think that would be beneficial to experiment and to try. Since this data, I mean, the distribution is way different compared to the phototourism dataset. I think it would be very useful to probably to fine-tune our current model on this data and to get better scores. I think, yeah, that's a good point.
Okay, thanks a lot. There would be one more question. Did you also compare the matches itself, for example, compared the matches which you get from, let's say, Superpoint or R2D2?
So you mean like to train one of these methods using our data, or
no?
What?
You, as far as I understand, you leveraged R2D2, right? Did you also try to use your technique with other local feature descriptors such as superpoint?
Yeah. So this work is still in the process. We are experimenting with D2Net at the moment. The superpoint model is also quite interesting, but the point is that originally it has been trained on grayscale images, and it's like questionable whether these stylized images could bring the benefit. I mean, could bring the improvement or not. So it's like a good point to investigate and to try. But yeah, at the moment we are just experimenting with D2Net, and yeah, but the work is not finished.
All right, then I'm happy to see more in the lines of this direction.
Yeah.
If there are no more questions, I'm happy to thank you again for presenting your work, and congratulations on achieving the second place in our challenge.
Yeah, thank you so much. Yeah, thank you.
With this, I would continue with our last speaker for this workshop today, Cyrill Stachniss. So it is my pleasure to introduce Cyrill. He is a full professor at the University of Bonn, and he heads the lab for photogrammetry and robotics. Before working in Bonn, he was a lecturer at the University of Freiburg in Germany and a guest lecturer at the University of Zaragoza in Spain, and a senior researcher at the Swiss Federal Institute of Technology in the group of Roland Sequard. Cyrill Stachniss finished his habilitation in 2009 and received his PhD supervised by Wolfram Burkhardt at the University of Freiburg in 2006. From 2008 to 2013, he was an associate editor of the IEEE Transactions on Robotics, since 2010 a Microsoft Research Faculty Fellow, and received the IEEE RAS Early Career Award in 2013. Since 2015, he is a senior editor for the IEEE Robotics and Automation Letters. In his research, he focuses on probabilistic techniques in the context of mobile robotics, navigation, and perception. Central areas of his research are solutions in the simultaneous localization and mapping problem, visual perception, robot learning, self-driving cars, agricultural robots, and unmanned aerial vehicles. I'm very much looking forward to his talk.
Hello, my name is Cyrill Stachniss, and I would like to welcome you here to my talk on vehicle localization. And I want to especially thank the organizers of this event to invite me to speak here. I want to talk about how we can use non-metric information to support vehicle localization. So in the end, we of course want to localize our vehicle in the metric space, but the question is, how can this non-metric information actually help us in our localization system? And the work that I'm presenting here is work that is done by several people from my lab, so a lot of the credits of what I'm actually presenting here is their work. And I want to start with arguing for using this non-metric information by saying that vehicles must operate under very varying conditions, and the world around us changes, and so its appearance. So we want to have autonomous cars or other mobile vehicles that navigate through the space and can estimate where they are. And for that, they need to deal with challenging situations. So what you see here are pairs of images, those pairs and those pairs, which have been taken at the same location but at a different point in time. And what you can see is that the appearance of the space has substantially changed. And the question is, can we deal with such strong appearance changes and still build a system that can localize or make the data association recognize the same place and saying, yes, this vehicle is at a place where it has been before. And that's what this, or the first part of this talk, is about. And just to show you that this is based on individual images, a challenging problem, I brought you a few pairs of images. And so let's see if you are actually able to identify if this is the same place, yes or no. So question, is this the same place, yes or no? I think that one is easy. It's a yes. We can see this building is quite distinct. Hold this flag. One image has been taken in summer, the other one in winter, but we as humans are still able to identify that. Let's go to the next example, this one over here. First would say, yeah, that actually looks pretty much the same, but it turns out, no, it is not the same place. It's not even the same street, it's a different street, but in the same neighborhood. And you can see it, for example, there's a tree over here, this tree is missing, but maybe they took down the tree, you never know, but it is definitely not the same place. And then I have the next example over here. Is this the same place? Yes or no? Again, it's a similar neighborhood. In Freiburg, if you drive around, you experience those images, but it turns out it's not it is the same place, although it doesn't look the same. And you can see it here. This building over here has been demolished, so the building doesn't exist anymore. The space appears different and looks different, but it's actually the same place. So it turns out that doing this recognition task based on individual images is quite challenging, but we can actually do that if we take sequences of images into account. So if we take into account that we have been recording one image after the other and we exploit this sequential information to align image sequences, this becomes a much easier problem. So they can use it in a localization system by exploiting this temporal or sequential information. And what I can do is, let's say I have one database recorded or one image sequences which I use as my database, maybe associate even with map information during a mapping task, which I recorded, let's say, in winter. And now I'm driving around in summer and I want to take just the image information and match them against the previously taken image. How do I do this? Let's say start with the most naive case. We build up a matrix where we compare every image of our query sequence with every image of our reference sequence. And we compare those images, for example, based on feature descriptors that we compute from those images, or any other way for comparing those images. And then we end up getting such a cost matrix over here. So bright values mean images look similar, dark values, images appear differently. And you can see just based on individual dark and bright values, it's actually hard to say where the vehicle has been. If you take the full matrix into account, so exploiting the sequence, you can see that here is a bright line going through this matrix. And this is actually the trajectory that the image has been taken. And by using this kind of full matrix, we can actually try to find a kind of path through this matrix. In this way, find the best matching pairs of images. So technically, we can build up a so-called data association graph. So a graph in which each node represents a data association, a match between two images. And then we can plan a path, the shortest path through this graph, which will give us the sequence of matched images. And the cost of this path, the cost of a node, is basically the cost a cost which is computed based on the similarity of those images. And through this path, through that graph, and by taking a local connectivity into account in this graph, we can actually exploit this sequential information. So that by planning a path, we'll find a path through this nodes, through this graph here shown as the red nodes. And in this case, a blue node is a so-called hidden node. There's a node along the path where we know the system has been there, although the images look not very similar. And this is something we call a hidden node, so something where we couldn't find a match based on an image, but based on the sequential information, we know the system must be here. And given this, we can align those image sequences and can align one trajectory with another trajectory, although those images have been taken under very, very different conditions. The problem that we have with this approach is that we need to compute this full cost matrix. And this is computationally expensive because we need to compare every image of my query sequence with every image in my database. And this is something which we can't do in real-world situations. So the goal is to bring this towards an online approach where we don't need to expand the full graph, but only part of the graph. The part which is shown or illustrated in green here. So if we only need to compute those green paths in there, let's say the most promising images, and then find a path in this, through this kind of promising region, then we may be able to do this in an online fashion. And we can actually do this, we can build up this graph on the fly so that we don't need to compute the full cost matrix, but only the cost matrix here shown in green, everything here in black actually doesn't need to be computed. So we want to avoid computing this part and only compute the green region so that we then can find an efficient path. And the question is, how can we actually realize this? How can we do this? And the goal, or how we can achieve this, is by simultaneously building up the graph during the search. So we don't build up the full graph first, we only expand those neighboring nodes that we actually need to compute. And in order to do this in an efficient manner, we need to have a good heuristic. So we know this from graph search, Informed search techniques such as A* are very efficient if we have a good heuristic. And a heuristic is a technique to provide a lower bound for the cost that will be generated if I go from a current node to my goal node, and I need to provide a lower bound estimate for that. And then I can basically turn into a lazy data association, traversal or building up of the graph, and expand only those nodes which currently look the most promising ones, and in this way expand only a small fraction of the graph, but still are able to find my matching sequence through that graph. If you think about informed search, you probably think about A*, but it turns out A* doesn't really work well. And the reason for this is that it's very difficult to design a useful and admissible heuristic. Admissible means you need to underestimate the cost and have a zero cost at the goal. And useful means that it's actually not just a zero function, it provides useful information. And this is different to a search in the Euclidean space, for example, where the straight line distance gives me a good admissible heuristic. Here we are in the space of image similarities, and here it is much, much harder to come up with a good heuristic. So what you need to do in this graph search, so you are in a certain node, let's say you expand it up to this node, and now another node looks more promising, like this one over here. Then in our data station graph, we need to estimate how expensive is it to go from here down to here and match the next L minus I images. And we have done this using a heuristic, which is not an admissible heuristic, so it's not guaranteed to provide a lower bound, but which takes into account the average cost of the best path found so far, multiplies it with a factor which is smaller than 1. So we say, let's say, we expect the best path to be only, let's say, 80% of the cost of the currently best found path. This is an assumption that we do in here. And then multiplied with the number of images. So we have our expected cost for an image comparison along a matching sequence. We have the images we need to match and this expansion rate, or this factor which scales the cost down in order to allow us to search, explore other alternatives. The problem with this heuristic is that it changes during the search because we find better paths, so we get better estimates of the expected cost, and this prevents us from the use of A*. So we have to modify our search algorithm a little bit to take into account that our heuristic may change during the search. But if we do this, we can actually perform this online visual localization of place recognition in changing environments. And you can see here our images. So this is our database images. You can see where this image has been taken and the current estimate of where we are. You can see here the vehicle is driving to a path that hasn't been mapped before, which is this road over here, so it doesn't find any match. But as soon as it re-enters known parts of the environment, it can establish the data association and can actually localize these images. And localize means here, through the matching with the database, we know where we are, and in this way can localize the vehicle just based on this image. Again, this is something which you wouldn't, of course, not use for a standalone localization system, but you may integrate this into an existing metric localization system to tell you where you are on a global scale or provide you with an alternative means to estimate your position on a global scale. And so this online search actually helps a lot to reduce the number of computations. So you can see here a rather large cost matrix from the vPrice challenge for performing this place recognition in those environments. And you can see here only a very, very small area in this graph actually needs to be explored. In this case, had only been 0.5% of the overall comparisons that need to be done. If you go to other very challenging environments, the number may be a bit lower, but you still only need to explore a fraction of the graph. So that you can actually run this on a real platform and multiple times per second perform those comparisons. You can again see here the current image, the corresponding database image, and here the part of the cost matrix that is actually computed and explored during the search. So this is kind of a zoomed in view of the expanded cost matrix, and you can see here how the system only needs to explore a small part of this matrix and actually finds the data association here. We can also do this, for example, over a day-night drive. So again, here we are driving at night and localize with respect to an image sequence that we have been recorded during the day. And even here under this strongly changing conditions, we only need to expand a small part of the search tree. And we can also show that we can find multiple hypotheses, can track multiple hypotheses over extended periods of time if we, for example, have two trajectories which look very similar. So that's actually an interesting thing, that just by exploiting this sequential information, we can quite robustly estimate image sequences, although the appearance of the environment has changed substantially. And again, as a short reminder, we have done this using purely visual information. No geometry has been used, no connectivity information except the sequential information, no odometry, no visual odometry. No cameras need to be synchronized. Really, the cameras are just exposed, let's say, 2 or 3 times per second. We have this image and just use these image sequences. And we can perform this localization just with this image information. This was, however, only part of the truth, so there are situations where the system can fail and may fail. And one of the reasons is if we have very flexible drive on flexible trajectories. For example, if we deviate from our originally taken trajectory and drive to a part of the environment where the system has never been. So then the system basically gets lost, re-enters the space at a later point in time. The question is, can we follow up on that? Or if we have taken shortcuts on our current route with respect to the reference trajectory. It's also something which currently cannot be handled. You can see it here in those cost matrices where this was a path I'm going, and then the system would actually need to jump over here and continue the search here. Or we have areas in my matching matrix where we can't find any match. These are those 2 areas over here where the system has been somewhere else. So if I, for example, run this in this first setup where there's no match here, this is a matching trajectory, and this is a matching trajectory. We will find the first one, or may find the first one. Well, finding the second one is just by chance. It's just luck, because we have been somewhere else, in an area which is not part of the map. This, however, is a problem which is not novel. This is something that has been investigated in the past. And one prominent example here is the kidnapped robot problem in Monte Carlo localization. So this is a AAAI paper from 2000. And what the authors here suggest is that if the sensor data doesn't fit to my current state estimate anymore, in this case a particle filter, a good idea is to sample new particle locations based on the observation model. So take the observation into account to sample new hypotheses to see if those locations do a better job. And so what we need to do in here is, if we kind of don't find good matches anymore, we need to find other places that are potentially good matches. The only question is, how do we actually find them? So how to find potential matches in this large database. So what we have done in order to do this is a technique inspired by locally sensitive hashing, where we use a hashing technique in order to find other potential matches. It's kind of a form of an inverted index, taking into account the different dimensions of the feature, binarizes those features, and then basically looks into the zeros and ones in the individual binarized dimensions, and then tries to find with an inverted index potential images that look similar to the current image. And it turns out that this is a very good technique to find potential re-entry points for my search. It's not that this hashing technique always provides me the best image or matching image. So what we do is we look for a certain number of potential matches, use those matches to expand, to create new neighbors in this data association tree search, and then through this similarity we have potential comparisons, compare those images, and if we find a good matching one, we can continue with this hypothesis. So again, we had this example. In this part of the environment, we have deviated from the trajectory, the system was lost, and the standard approach really failed, so it only found this part of the trajectory, and then just by chance the last one, but this was just actually good luck. But everything else doesn't really work well. And if we use this hashing technique, so whenever we can't find a good match, we use this hashing technique and see if we can find re-entry points somewhere else. And it turns out that the system is able, with this hashing technique, to say, I don't find anything up here, then finds the correct re-entry point here, localizes the system appropriately, then it gets lost again, it starts sampling. See, there's these blue dots over here, probing locations, but they're not very promising, so it doesn't expand them further until it finds gets an image which is similar to a place it has been already. And then at some point in time, the hashing technique actually finds the re-entry point, expands the search, and I'm actually able to localize my system. So with this hashing technique, I'm actually able, in a lot of very situations, actually find those re-entry points, relocalize the system by just creating a few new neighboring edges in this data association tree. And I can use this also to, for example, localize along multiple trajectories. So if you have multiple reference trajectories, not only one, you can use this hashing technique to simply find re-entry points in multiple of those trajectories. And I just brought you a few examples how that actually looks like. So this is a trajectory, with a query trajectory taken with a car, and there are several, I think in this case 3 or 4 trajectories had been taken before, recorded, and then the system localizes the trajectory that I'm currently driving with respect to the query trajectories. And you can see here the correct matches in terms of in green, and wrong ones, which are false positives or false negatives, where the system missed an image, but through the sequential information, of course, can recover its position and knows where it actually is. So that if I then compare where I was driving with the trajectory I've been matching to, we can see that, of course, we only need to find one color. As long as we found the correct color, everything was done well. So here I was localizing on the red trajectory, then I switched to black, and then here to the cyan trajectory, because this was the most similarly appearing place in this scene. We can go a step further and actually use street view images and localize a dashboard camera using street view images. So in this example, we just recorded a data set in Kiev, driving through Kiev, and matched only against street view images. By extracting image sequences, virtual drive through street view, I'm actually able to localize my camera in my car in this environment. And that's actually very nice, because this is much closer to a map, because I can just use existing image material just from street view in order to localize myself, my vehicle, in this environment. And you can also see the trajectories that we recorded, and then matching this against the generated sequences out of Street View, so they can actually localize in the Street View data. I can even take this a step further and start taking a random YouTube video, and so nothing we have recorded on our own, something we just found on YouTube, and localize it against Street View images. So we can take videos we found randomly on the web from dashboard cameras, which a lot of people upload, and actually localize those images. Again, I don't have ground truth information over here, and doesn't work as well as with the trajectory that we had recorded, but you can see that you can localize a large number of frames that you found in this YouTube video actually within this within the Street View images, which is actually a very nice indicator that this is a robust system for localizing these sequences of image material. So as a short kind of summary so far, what we have done, we proposed a system for visual sequence-based place recognition that exploits the sequential nature of the data and works in changing environments. So in different seasons, matching current images against Street View data. So even if the environment has changed substantially, we can do this in an efficient way. And we can do this in online fashion, build up this graph on the fly, dealing with multiple trajectories, and also the hashing approach really helps us whenever the system is lost or is deviated from that trajectory. And the next question is kind of now, most of those cars actually have laser range data on board as well. So can we use laser range data to do something similar, to localize with this data? And it turns out, yes, we can. So this approach is slightly different. So we could use this data association graph idea as well for the approach here, although we haven't really done that because this work started as a technique for improving loop closing in SLAM. So whenever you build a map of the environment and localize yourself in the map, which is called often simultaneous localization and mapping, then you want to find those re-entry points, those loop closing points, and you can use a place recognition system for that. So this is an example. We have two 3D scans of a car. One, the car is driving around here. The other one, the situation is driving down here. And the question is this the same place? And we can rephrase this question as, do actually the 3D scans overlap? And if those 3D scans overlap, I should be actually able to find a loop closure over here. And I want to focus on this question: do these 3D scans overlap here? And scan overlap, or something that is an older technique from photogrammetry, where you look into images or image overlap, and we just use this on range images that are taken from a 3D lidar, such as a Velodyne or an Oyster scanner. So we have a scan A and a scan B, and if we kind of put the scan into the same location, we typically generate a higher overlap between the scans, or get a higher overlap, rather than situations where they are not aligned. And again, this overlap has no idea where those images have been taken, but you want to estimate what's the potential, what's the overlap between this scan. And what we have done here is actually using a neural network-based approach, which is fed with training data of images taken at similar locations and from other locations where scans overlaps and don't overlap, and tries to estimate this overlap. And that's a technique that we've presented at RSS this year, and it was a technique for finding loop closures. Again, not using any metric information for finding these loop closures. And how the system works, just kind of in 20 seconds, we have different information, such as the range information we have from our scanner, normal information, intensity information, and also semantic information that are estimated from a semantic segmentation system from those 2 scans that we have been taken. And then there is a Siamese network with the 2 legs over here, and then there are 2 heads. One estimates the overlap between the scan, and the other one estimates the yaw angle, so the rotation around your yaw. And then gives me an estimate on how similar those scans are. Again, there's some pre-processing involved in terms of computing normals from the intensity image, taking this information into account. Then we have our network structure, the overlap network with the 2 legs and the 2 heads, which then provides me with the output information. So what I get is an estimate of the overlap, so how much do the scans overlap, and what's the yaw angle rotation among them, and so that I can use this information then for finding loop closures in the context of SLAM. And that's something that we have done, integrated this into Zuma, one of the LiDAR-based mapping systems that have been developed by Jens Belay from my lab. And what we can see here, so the blue thing is a standard loop closing technique so far used in Zuma, and the green curve is the approach with this overlap network, not using any geometric information, and the red one is this overlap network if we take the pose uncertainty that we have in our SLAM system into account as well in order to find those closures. And so this overlap net can be used for lobe closures, so for doing place recognition based on 3D LiDAR scans, without using metric information tells where we are right now, but of course there's metric information in the local scan. And what overlap net does, it predicts the loop closures also in very challenging situations where you have very little overlapping areas, where current loop closing systems typically fail, and is now part of our Zuma system. And the question that we have after we have developed this work for RSS here is kind of, can we use this idea of overlap for localization as well? Because it is very similar to a place recognition system, so how can we actually integrate this, or can we integrate this into a localization system? And we started here out with good old Monte Carlo localization, so a particle filter-based localization system, which basically has 2 steps. It takes a sampling from a motion model, so where's the system at the current point in time, given we know where it's been before, and some odometry command, and then the correction step of this recursive base filter is done with the observation model, so the likelihood of the observation given the pose and the map. And for computing this observation model, we now want to take the overlap net into account. So we use this idea of overlap, so we put in our query scan, the scan that we currently have, and a map scan, so a scan that has been taken at the location when we were building the map, and then compute this overlap. What we can also do is, what we do in practice, we build actually a 3D model of the environment in the mapping phase, and then generate virtual frames at different locations in the environment, just on a small grid. So that's those map scans, actually pre-computed scans, taken at different locations based on back projection. So we need to compare them, and this is an operation which is done on a per particle basis, or for particles that are very nearby, we can actually group this operation so that we are then able to compute an observation likelihood for that particle using this idea of overlap net. And so we generate those, in this example, a map for all those blue locations here, this kind of virtual scans. So if we kind of zoom in, there's the area have been taken, we put a grid on this, and then can, as an example, take 3 locations over here and practice as a 20 centimeter grid, and then compute virtual scans, store them in the map, and use them then for the comparison. So we have kind of those map scans, and then we need to compare those, the query scan to the map scan of the individual particle. So every particle will generate one of those map scans and be compared to our actual scan. And then we can use this overlap net architecture to actually come up with an observation model that we then can use in Monte Carlo localization. And again, these are kind of rather fresh results. We can then use this in order to estimate a vehicle. So we do a localization. You can see the particle filter over here, converges successfully after a small amount of time. And then we take the current 3D scan that we have, take the generated map scan, and then can perform particle filter-based localization system and track the system over time. And again, just using this information that is obtained kind of in a kind of topological way. And this is again done only with this with the 3 LiDAR scans, not taking other information such as visual information or other things into account over here. However, if we go to real autonomous vehicles, then we typically have maps that may look like this. So this is an example from a map used by one of my collaboration partners. 2 of my PhD students that I mentioned in the beginning work for Volkswagen and work on localization there. So there's a map where you have certain features or poles, which you can see, lane markings, and you want to localize in this map using your data. And what you typically do, you do kind of a local data association between what you see right now and your environment. And then often to make that robust, there's a map matching step involved. So you take the full map and perform a full match of that map. This, on the one hand side, allows you to recover from failures quite quickly, and this is similar to this kind of more global approach where you could also use image information to see if you have deviated from the trajectory and the system hasn't realized this. Then a temporal smoothing is involved in this case. It's not a particle filter, it's a graph-based or vector graph-based approach in order to perform this estimation. But the steps take the sensor data into account, doing local data associations, but you can fuse this global information in there as well. And how this online optimization can be done in an efficient way was the work done by Christian Meerfels. It's a sliding window optimization approach he developed it for postgraph, but you can transfer it in the same way to vector graphs. It's a black box integration system where you can have different post information or post sources you can put in and very seamlessly integrate visual odometry, laser-based localization, place recognition just into that system by fusing this into this post graph. By today, we transformed this into a vector graph representation, and you have those vectors between the nodes you want to estimate, such as landmarks and vehicle positions, or can even be map reference frames. And one of the key things is here you can have GNSS involved, but you can also have these alternative sources in there, such as the localization capabilities of place recognition systems I've explained before, and you can feed them in the same way like you would do with a GNSS node. So that in the end, you can actually realize a localization example. So this is an example by Daniel Wilbers, doing this at Volkswagen, where you use all this information that I've presented. You build up this graph on the fly. You fuse in data for matching poles. You can also integrate visual information and other sources in order to localize your vehicle and do this in an online fashion and estimate within a few milliseconds where your platform is and integrate all those sensoring information in order to localize your vehicle. With this, I come to the end of my talk today. So what I hopefully have shown you is that you can use image data and LiDAR data for place recognition and vehicle localization. So I talked more about the place recognition part, but you can integrate it into the localization system itself. Sequence information helps, especially if the environment changes substantially. I think we've seen this nicely in the first part about image localization, and those topological information helps me to also localize the system metrically and can be quite elegantly integrated through this vector graph optimizations. With this, I come to an end. I would especially thank Olga, Reini, Jens, Christian, and Daniel for their contributions to this work, and also for all the parts I talked in the beginning, except of the last part. Everything is available as open source, so you can download this and try the stuff yourself. So I hope that was entertaining and you enjoyed this talk. Thank you very much for the attention, and I wish you a nice remaining conference. Thank you very much.
So I would like to thank the speaker for the great talk. Thanks a lot. Now I'm happy to take questions. So from the audience, if there are any questions, feel free to ask. I would start with the question. First of all, welcome Cyrill Stachniss to the workshop, and thanks for joining the Q&A session. It's my pleasure to host you here.
Thank you.
I would have one question on the visual sequence based place recognition part.
Yeah.
So the question would be, you're building a database. How large can this database be, or basically would it also scale across cities, or how big can it be?
I mean, in the end, the only thing you need to store in the, let's say, for illustration purposes, you would store the images at different locations, but in the end, it depends on the feature representation that you choose. So initially, we started as very compact, small features, which just take, I mean, a few kilobytes. Right now, or the last thing we had been using in here were a certain layer of the NetFlat architecture, where you store one layer of that architecture as a feature, and you actually need to store only this this feature information in your database, plus some bookkeeping information. I mean, for example, where you have been while you've been recording the images in order to refer back to a metric space. But that's actually it, and you don't need to store much more. So we're talking about database. In the end, we just stored that basically on disk with an index file. That was nothing very complicated. And for the hashing infrastructure, need to store this inverted index, but there's also something which is not very critical. So from the storage point of view, never was a limiting factor in this approach. But of course, we haven't scaled that up to, let's say, country-wise or state-wise scales. This is nothing I would claim here. We really kept that inside a city and used a couple of sequences, can even be multiple kilometers long, multiple trajectories, but not really scaled that up to hundreds or thousands of kilometers. But I think the storage grows linearly, and this shouldn't be the limiting factor in here.
All right, thanks a lot for answering. There would be another question regarding, would the graph-based matching approach benefit a lot from image database taken by a mix of day and night images? Maybe one addition, because by design at night, it tends to compare images with night images and day with day images.
Of course, you can actually do this, and this are basically techniques that people from Paul Newman's group in Oxford have been done, this experience-based navigation, which basically has a similar graph, or has a topological graph structure, where you store explicitly links saying this is the same place taken summer, winter, rain, whatever, and then you can localize against this. We haven't stored this explicitly, but we have taken multiple trajectories over different points in time, summer, winter, rainy season, whatever it is, and we just store the raw trajectories. And the hashing technique allows us actually to make links also in the database, for example, between the summer and winter images, even the database images. And we know that they've been recorded at the same place. So the approach will actually automatically pick out the images which look most similar to where we are. So we don't need to do that explicitly, but of course you can exploit the information. You may even be in the situation where you say, we know that it's currently nighttime and we only want to match against nighttime images. We haven't done that, but you could easily integrate this if your system, for example, generates too many false positives, as an example. But we haven't done this explicitly because it wasn't needed, and we had the more elegant approach that we don't need to do this classification. We just need to put in the raw data itself, and that was kind of useful. Worked well.
Okay, great. Another question would be, do you think the relative poses from odometry system like visual odometry or wheel odometry can improve the graph searching method for sequence matching?
Yes, definitely. So what we have done, when we built up that system, and this work started in 2014, something like this. What we wanted to avoid is that we have a system where we need to calibrate everything. We have a camera calibrated with the odometry of the system and everything. We just want to have raw camera images recorded in the most stupid or most naive possible way. And so this is how the overall work started. What you, however, have in that graph is you need to define the connectivity between the different layers. So if you're in one layer, to which to how many nodes in the subsequent layer are connections being created. And if you know how fast you're going and you have metric information, you can of course reduce the number of connections you may need to when you go into the next level. So we are currently basically, let's say, need to do an overestimate by taking too many branching factors in this graph search into account. So if you have better information about your current velocity or your movements, you can dramatically reduce the neighbors that every node have, and this will speed up your search. So you can definitely do that. The system that we developed was kind of running on a notebook from 2015 with 2 Hertz approximately. So that was good enough at that point in time, but you can definitely speed this up, and exploiting this information definitely helps. I also have to add to that, of course, in the end, you don't use this visual localization system as your one and only localization system, not at all. So it's just one additional source. So your underlying state estimation system, which could be, as we have seen, a histogram filter I've seen today, could be a particle filter, could be a vector graph. I would probably, if I build a system today, go into a vector graph or a graph-based representation as the underlying optimization framework. And there you will fuse your visual odometry information as an additional source in there. So it will definitely help the overall system, and you should definitely use this if you want to metrically localize your system. The place recognition is just kind of an additional global source which adds additional information to this. For example, that you may not need to use GPS information. So in the example that I've shown, except the last video, for example, no GPS information at all was used, so that the system can still globally localize. But of course, the more metric information you have, let it be from visual odometry, from your wheel encoders, integrate into your system. Not using it would be dumb, and you get better and you get more precise. And you can infer that you haven't jumped 50 kilometers away because you know that 2 seconds have evolved since the last point in time, and not using this information would be stupid. But the visual approach explicitly didn't take it into account. We, of course, wanted to build an easiest possible system. But yes, it will help. Yes, you can do better.
All right, great. Another related question regarding deep learning. Can hashing technique be improved with neural networks, and what is the prospects of that to improve querying and retrieval?
Oh, that's a good question. I haven't really thought about that. So we were using quite simplified hashing. So there are several ways you can do. You can use this locally sensitive hashing. We started with a different approach, which was basically a self-created technique at that point in time, where you binarize your features and basically count certain dimensions if they have, or you check if they have a 1 or a 0, and then you create an index where, for example, if dimension 1 has a 1, you store the images in a list which have, or in a data structure where this dimension is 1, and you do this for all the different dimensions. And let's say you have a 200,000 dimensional feature vector, for example, then you have this 200,000 dimensions and basically the index in there. And then you just need to go with the query image over this binarized vector and see which lists remain. Just make a counter, and then basically get the ranking of the images based on how many counts you have, which you can do very, very efficiently. So in the end, so doing this comparison, the sampling technique in the databases was in the order of 500 microseconds that it took. So half a millisecond, and that was really great. So it was really optimized for speed. Locally sensitive hashing worked similarly well, but took substantially longer for executing this. So there was not really the need to go into a learning technique for that, but probably you can get a bit better and then get better, get out better hashing results, so that more results are closer to the images that you had. But this is just a random guess. Nevertheless, take into account the features that we used within this hashing technique were actually a feature which stemmed from a CNN. So there was learning involved, but there was no learning involved in terms of the hashing function itself. You could get better, but this would be really random guessing from my side because we haven't investigated that at all. And I'm not experienced with learned hashing functions, so I probably should ask someone else than me.
All right, great, thanks. Another question we have from is how to deal with drastic structural changes in the environment, and how can we model this?
What exactly are?
I mean, I guess
with
structural changes. For example, for example, if a building is there and the building is missing a few months later, and then you want to revisit this place and or a construction zone or kind of these things, I guess.
Okay, so this is not that much of a limiting factor. And the reason for this is that you take this sequential nature of the data into account. So you will always have individual images which don't match. These were those things which I've always illustrated in blue, this so-called hidden nodes. And you can obviously see this, whatever you're driving around the city, you have a big truck in front of you, which takes 80% of your image, is filled with a truck. The place will look substantially different. The same as if the house has been taken down or demolished. And just through the sequential information, you're actually able to figure out that you must have been at the same place. You have images matching before, images matching after, and they have maybe 3 images which didn't match well, but given the way you've traveled, it must be there. So from this point of view, I think that's not hard, and this is actually something that the approach covers quite elegantly if you have this sequential nature. What, however, gets a bit more complicated if you, let's say, have construction sites which deviates on the trajectory. So you're basically routed to a completely different place, something which hasn't been mapped. But this is then basically a kidnapped robot problem where the robot is basically taken away, and it's not even taken away inside the map, it's actually taken outside the mapped or the mapped area. And then localization is very hard, and you basically can't localize yourself if you haven't seen any map data and you don't have any GPS or something like this. But what you want to be able in doing is actually, as soon as you re-enter the known parts of the environment, you want to be able to localize quite quickly. And therefore, the hashing technique was actually designed to exactly solve this problem of finding the re-entry points after kidnapping the platform, or driving a trajectory where the system has never been before and there's no map information available. So finding this re-entry point is then the part. And so, yes, this works. So local structural changes through the sequence information. And if you deviate to a different part of the environment we have never been, I mean, no map will help you. Then your goal is to quickly find the re-entry points, and there hashing helps.
All right, great. Thanks a lot for all your answers. I think there are no more answers from the audience. Yeah, let me check. I think, yeah, we have covered almost everything. Yeah, thanks a lot for answering the questions and having you here in this workshop. It was my great pleasure to have you here, and I hope you enjoyed it as well.
I did. It was also a pleasure to show up here and talk outside my core field in terms of conferences. So thank you very much for this invitation. I highly appreciate it.
Thanks a lot. So with this, I would like to conclude our workshop for today. I would also like to thank all the other speakers of this session for the afternoon. And one point to mention is that all the talks from most of the invited speakers are even accessible online from the ECCV platform. So if you're interested in talks, please go and watch them again. And also, I guess, please don't hesitate to reach out if you have further questions. So thanks a lot for being here in this call, and wish you a nice conference.
Thank you very much. Thanks for the organization as well to you.
Yeah, thanks a lot, and yeah, have a nice day or evening wherever you are.